Oh, I told you about the example service. You haven't seen that. No, I haven't. Did it work? Yes. So what I can see that is Godzilla result. So he shows that in the Laplacian case, if you have a pair PST, there is it also helps. The last time I read the bed for this class. Okay. There is no photo. Right. In the same class. So don't be class test. You want class EJ. Yeah. So you want minus EJ to E2 minus E3. So in that pair also we have we have 5/2. So I wonder, so you have to send that between these two plus states, you can have the state transfer at I think at 5/2.
Yes. Yeah, that's right.
So if the case is the same, then I think we should just see between.
Almost the same photo. Yeah.
Because the pair set transfer from Q1 minus EJ to minus EJ. The class state transfer from Q1 plus EJ
One sheet or two sheets?
to plus EJ, then we can sum it up.
Oh, I got it.
Then also the part of set.
Okay, so then I think maybe the place that I want to do is maybe not.
No, this one, another
Maybe the
one.
thing to do is start looking at threshold graphs.
Read about
Classing
about grammar and
yes,
things.
there's can characterize the threshold graphs. And so it may be, so that would be for I pair or possible. Yeah, a necessary condition we already have. Or checks, so that would tell us the family of threshold graphs.
Good morning.
Reverse engineer.
Now, I want somebody to connect it. Yes, sir, I am really missing it.
So I remember
Yeah, go ahead.
the Gaussian.
I think what Steve
threshold
said
graph.
just now, if you don't watch your emails every day, you will, that's not saving today. Because if so many emails come, you're not
Somewhere in there,
saving.
it's gonna be for there.
Connect it, okay?
Our definition is.
Because last time, once you have logged
In
in,
terms of the.
so once you session, it will automatically.
What did not do in my guest house? Guest house.
Threshold graph. Anyway, so we could take a look there.
Yeah, yeah. Because that is interesting, same pair, that class of from plus difference.
Yeah.
So let me make down from is given.
Good observation. Yeah. I mean, what I find. Curious about it is, example, right? Say the plus state. That goes to 2 inches.
Those are, here's my BSc scholarship.
So more interesting.
What's your name?
One J1.
Actually,
So trans.
shut it off.
No, I
No, no, yeah, I'm just joking.
Say
Well,
one.
that's your off.
Well,
that one part of your name.
Perfect state trans.
Yeah. What's the reason? Give you a good, get supervisor. Work hard. Your job is to work. Don't depend upon him to write paper.
She's very much into research.
Yes, and please, books, please, for God's sake, don't just read papers.
Yes.
My first advice to my students is read good books thoroughly, word to word.
I mean, this thing, so there we have twin versus, I think. Geography, the
Yes,
temperature.
but it's not one paper. Yeah. Like it, we see to read it, but we said, so there's no.
So in my paper, so that I have, my first conversation with you, the twin versus, in a computer, people remove matching.
Yeah, so.
It means two disjoint edges you remove.
Good books.
So for each case, if you remove an edge, then between the invertices, we have PST.
See, they're all things.
And so if you remove another edge, then there also we have PST.
Right.
This we can do repeatedly, but
On somebody
I mean,
else.
I think that should be.
So he will be like, oh, can you be used?
So they get, you can have it.
That's my only.
So in that,
Yeah.
and on PST, so we can find this thing, but I don't know. Yes, from you want to.
But don't get what we.
I mean,
Read it or
I can do the like, you want it next time.
Yeah.
Yeah, also I can do it.
Okay, so that's the way to look at it. Try and get some understanding of this perfect state transfer. Matrix states and use those structs plus states.
This is natural to, necessarily, complete graphs, but I don't know about special graphs in general, or in other kind of graphs.
Right. Right, okay, that seems like a good idea. Let's concentrate.
Yeah, yeah. Yes, I'll see to that, and
And yeah, right now we should find out. I'll try and think about it, yeah, as well. I have a very long journey home. Yeah, we'll picking up a plan.
We're here for a long time, like you say.
Yes, yeah, 30 hours, so we haven't been to hear back. Good, thanks.
Not collected?
It doesn't look like.
Another question.
It is a book, it's a very good book. And you can work on that. You put back and that's good. I would like to visit that place if they want.
నాకు బ్యాగ్ తెచ్చేది ನಿಮ್ದು ಬರ್ಲಿಲ್ಲ ಮತ್ತೆ ಸೆಕೆಲಿಕ್ಕೆ ಇದು ರಿಜಿಸ್ಟ್ರೇಷನ್ ಅರ್ಜಿ ಬಂತು ಆದ್ರೆ ಮತ್ತೆ ಒಂದು ಸರ್ಟಿಫಿಕೇಟ್ ಬೇಕಂತ ಕೇಳಿದ್ರು.
Only outflow back.
Okay, we can go through the Google thing that.
Yes.
Browser is not
Here it is.
Oh, you got it.
Yeah, but.
In Google.
Yeah. Yes, which is what.
It's much in the zooming will be there.
Yes, so. That's. Be kind. Yes. I'm sure they got the person.
No, you don't get good. Good morning.
Good morning.
Morning.
From. Be kind. Okay, because it's done.
Shashwat, they didn't start from there. They didn't start from Woodcock. Oh, I didn't bring my boy. Yes, sir. 9:22. 9:21. 9:21. Okay. ಇನ್ನು ಬಂದಿಲ್ವಾ ಅಥವಾ ಬರೋದಿಲ್ಲ? ಕಮ್ಮಿ. ಅಲ್ಲಿ ಹುಡುಗರ ಕೈಯಲ್ಲಿ ಸೂಟ್ ಕೇಸ್ ಮತ್ತೆ ಮತ್ತೊಂದು ಬ್ಯಾಗ್ ಇದೆ. ನನಗೆ ಸೆಷನ್ ಆದ ತಕ್ಷಣ ನಾನು ಮಾಯ ಆಗ್ಬಹುದು.
ಕಾರಿಲ್ಲೇ ಬರ್ತದಲ್ಲ
ವೆಜ್ ಸ್ಯಾಂಡ್ವಿಚ್.
ಯಾವ್ದು ಹೊರಡುವ ಕೊಟ್ಟಿರ್ಬೇಕಲ್ಲ.
ಹೌದು, ಈಗ ತಗೊಂಡ್ರೆ ತುಂಬಾ ಬೇಗ.
ಹೌದು, 10:15 ನಾವು ಕಳಿಸ್ತೇನೆ.
ಅವ್ರ ಏನು ಗಾಡಿ
Eleven o'clock,
Plain
huh?
request or grilled one?
10:45 will be 10 minutes. Cafe will be there today, Saturday.
Oh,
Nitish,
Saturday.
cafeteria is open today.
Saturday then. Third Saturday.
Not working. Then we have to tell.
They'll come get the tea, no? By the time they're there, yeah.
ಅದು ತಡ ಆಗ್ತದೆ.
ಇಲ್ಲ,
ಟೀ ಜೊತೆಗೆ ತಗೊಂಡ್ ಬರ್ಲಿಕ್ಕೆ ಹೇಳಿ.
ಅದೇ ಟೀ
with that.
ಟೀ ಒಟ್ಟಿಗೆ ತರ್ಲಿಕ್ಕೆ.
One enough or? Sadiq should come.
No, Prakash will tell, no?
Prakash mostly might have started there. I will tell Prakash.
Prakash, just call him.
ಯಾರ ಹತ್ರ ಕ್ವಶನ್ ನಂಬರ್ ಇದೆ?
ನನ್ನ ಹತ್ರ ಇದೆ. ನನ್ನ ಹತ್ರ ಇದೆ.
ನೀವೇನು ಬಿಸಿ
ಇಲ್ಲ, ಅವರು
ನೀವೊಂದು ಫೋನ್ ಮಾಡಿ.
ನಿಮ್ಮ ಮೊಬೈಲ್ ಕಾರ್ ಇದೆಯಾ?
ಅಲ್ಲ, ಅವನು ಅಲ್ಲಿ ಹಾಲಲ್ಲಿ ಬಿಟ್ಟು ಬಂದಿದ್ದಾನೆ.
ಅಲ್ಲಿಯಾ?
ಪ್ಲೀಸ್ ಗೇಟ್ ಬಂದಿದ್ದಾರಲ್ಲ.
ಹಲೋ ಹಲೋ ಸರ್, ಅಂತ ಹೇಳಿ ನಿಮಿಷ.
ಕೃಷ್ಣ, ಯಾರು ಫ್ರೀ ಆಗಿ ಬೇಗ ಬರ್ತಿದ್ರಿ ಇಲ್ಲಿ? ನೀ ಬರ್ತಿದ್ಯಾ? ನನ್ನ ಮೊಬೈಲ್ ಅಲ್ಲೇ ಎಲ್ಲೋ ಇದೆ. ಈಗ ಪ್ರಿಂಟ್ ಸರಿ ಬರ್ತಾ ಇದೆಯಾ? ಅಲ್ಲ ಪ್ರಿಂಟ್ ಎಲ್ಲ ಸರಿ ಬರ್ತಾ ಇದೆಯಲ್ಲ ಈಗ ಪಕ್ಕ ಅಲ್ಲ ಎಲ್ಲವುದು? ಓಕೆ, ಥ್ಯಾಂಕ್ಸ್. ಮತ್ತೊಂದು ಇದು ಪಾರ್ಟಿಸಿಪೆಂಟ್ಸ್ದು ಅದು ನೀನು ಗಡಿಬಿಡಿ ಮಾಡೋದು ಬೇಡ. ಆಮೇಲೆ ಬ್ರೇಕಲ್ಲಿ ತೆಗಿಯುವ, ಒಮ್ಮೆ ನೋಡ್ಬಿಟ್ಟು. ಇದು ಅಷ್ಟೇ, ಯಾವುದು ಆರ್ಗನೈಸರು ಅಷ್ಟೇ. ಮಧ್ಯಾಹ್ನ ಆದ್ರೂ ತೊಂದರೆ ಇಲ್ಲ. ಅಕಸ್ಮಾತ್ ಆರ್ಗನೈಸರ್ದು ಇವತ್ತು ಆಗದಿದ್ರು ನಾವು ಕಲೆಕ್ಟ್ ಮಾಡ್ಬೇಕಾಗಿಲ್ಲ. ಎಲ್ಲರಿಗೂ ಒಂದು, ಯಾಕಂದ್ರೆ ಟೈಮ್ ಶಾರ್ಟ್ ಇರ್ತದೆ, ಎಲ್ಲರಿಗೂ ಒಂದು ಥ್ಯಾಂಕ್ಸ್ ಹೇಳಿಬಿಟ್ಟು ಮಾಡಿ. ಅಲ್ಲಿ ಮತ್ತೊಂದು, ಹಲೋ ಕೃಷ್ಣ, ಅಲ್ಲಿ ಅಬೌಟ್ ರಾಮಾನುಜನ್ ಒಂದು ಪ್ರಿಂಟ್ ಇದೆಯಲ್ಲ? ರಾಮಾನುಜನ್ ಅಲ್ಲ, ಇದು ರಾಘವನ್. ನಾನು ಪ್ರಿಂಟ್ ತೆಗೆದು ನಾನು ತಗೊಂಡ್ ಬರಲ್ಲ, ತಗೊಂಡ್ ಬಂದ್ಬಿಟ್ಟು. ಥ್ಯಾಂಕ್ಸ್.
ಒಂದು ಪ್ರಾಪರ್ ಫ್ಯಾಕ್ಟ್ರಿ ಅಂದ್ರೆ
ಮಾಡ್ಬಿಡುವಲ್ಲ,
ಪ್ರಕಾಶ್
ಇಲ್ಲ ಆಗ್ತಾ ಹೋಗ್ತದೆ.
No, the first one is writing second. First one, yeah. Next to the building, you get up and the third one. Then here we can get after that.
What place?
Not, but yeah, they have many birthplace for the English white very much. They are not because.
So how will you know?
English white. Be renting an apartment. For the 4,000 an apartment. She was living alone in a small apartment. I have this picture. On routine, I did over 1897 years. I will go and process it. Because picture. More than China Lake and one.
ಮೇಡಮ್ ಅಡ್ವೈಸ್ ಏನು ಇದು ಮಾಡ್ಬೇಕಂತ? Elected has not come here. I noticed that you cannot be there still there, it's up to what you used to hear.
If you show me the book.
So after taking, you know, the company is ready to come to this. The famous, copy, yeah. But those book was not easily available. No, sorry, but it's like everyone. So this is something significant. No, madam,
Call me, I will tell you. No.
There is some issue.
Today evening, only to.
Yeah, thank you so much.
That time, evening also, you have given to.
Okay.
But he had to wait, right? After this one, we'll talk. Even they told.
Then you also will go with me. I will go by my bike actually. Yeah, right. And actually want to go in Malaysia. All right. Okay.
Yeah, we will. You have absolute kind of.
ఎంత ಬೇಕು ಗೊತ್ತೇನಾ? So we are going to what we are sourcing that was by car, super moon. अच्छा जल्दी हो गया तो I was दूध का गोवा we cannot go there. Even the calls is another. Another successful. ಚೆನ್ನಾಗಿದೆಲ್ಲ Yes, I said
Very good morning to one and all. God is revealed through mathematics, said Srinivasa Ramanujan. With this inspiring thought, on behalf of Karams and Manipal Academy of Higher Education, I warmly welcome you all to the event remembering the legend Ramanujan. Today, we pay tribute to Srinivasa Ramanujan, whose exceptional contributions continue to inspire generations. Let us start by lighting the ceremonial lamp and offering floral tributes to his portrait. I kindly request convener Dr. K. Manjunatha Prasad to escort the dignitaries for this auspicious ceremony.
First flower.
ದೀಪ
ಹಚ್ಚಬೇಕಲ್ವಾ?
ಹೌದು ದೀಪ ಹಚ್ಚಿಕೊಳ್ಳಿ
ಲೈಟ್ ಆದ್ಮೇಲೆ ಕೊಡಿ. Please. No, yeah, first. Let us the lamp and yeah. Okay, one of it. Okay, I'll get.
I told him that he should not put the bank. That's why I. The floor?
Yeah, the flower you can put.
I'm traveling. You too. Okay.
I was glad of time.
Yeah.
Yeah, you're all done. You're speak now. Yeah. So we should stay here, I think. No, you can go to speak now.
What is it? Yeah, please. Yeah. What does? You need to just
Begin the program, we will reflect on the extraordinary life and mathematical legacy of Srinivasa Ramanujan. I now invite Dr. Harikrishnan PK, Organizing Secretary ICLAA, to kindly address the gathering and speak about the life, work, and timeless contributions of Ramanujan.
Good morning, all. Srinivasa Ramanujan, born on December 22, 1887, in Erode, India, emerged from modest beginnings to become one of the most remarkable mathematical minds of the 20th century. Largely self-taught, his deep intuition and singular dedication to mathematics were evident from an early age. Guided by an almost spiritual reverence for numbers, he explored patterns and relationships that eluded others, filling notebooks with thousands of original results in number theory, infinite series, partition functions, continued fractions, and elliptic integrals, many without conventional proofs. Despite limited formal training and the challenges of poverty, Ramanujan's genius soon attracted attention. In 1913, a letter to the eminent British mathematician G.H. Hardy, containing a remarkable collection of theorems, led to an invitation to Trinity College, Cambridge. In England, his collaboration with Hardy flourished. He published influential papers, expanded the theory of partitions through the Hardy-Ramanujan asymptotic formula, and advanced areas of mathematical analysis that continue to underpin modern research. In recognition of his extraordinary contributions, Ramanujan was elected as a Fellow of Royal Society in 1918, one of the youngest and most distinguished in its history, and was also made a Fellow of Trinity College, Cambridge. Ramanujan's life was tragically brief. After a prolonged illness, he returned to India in 1919 and passed away on April 26, 1920, at the age of 32. Yet his legacy endures. The notebooks he left behind continue to inspire mathematicians, and his insights resonate across diverse fields such as number theory, combinatorics, and even contemporary physics. Today, as we gather just days before December 22, India's National Mathematics Day, we honor the visionary legacy of Srinivas Ramanujan, whose brilliance continues to inspire scholars and learners alike. In 2012, the Government of India formally designated Ramanujan's birthday on December 22 as the National Mathematics Day, celebrating his extraordinary contributions to the field and marking 2012 as a National Mathematics Year in his memory. May this gathering reflect that same spirit of exploration and remind us that mathematics is more than a subject. It is living journey of curiosity, creativity, and insight, just as Ramanujan showed us. Thank you.
Thank you, sir. Now, with great privilege, I invite Professor T.E.S. Raghavan to share insights on Ramanujan's fascinating works.
Is all right?
Yes, yes.
Okay.
But we have to come up with something.
Yeah, I can keep, okay. Uh, I personally knew Ramanujan's wife. She used to live 4 or 5 houses away from my flat in Triplicane. Triplicane is a place where I grew. And I was staying in 32 South Tank Square. Hers was the Periam, which was 4 or 5 houses away from my apartment. I used to go each time on the 22nd of December and then look at this picture and prostrate before Ramanujan 8 or 10 times. And then she used to give me a copy of the collected works of Ramanujan, and I used to choose this particular one to explain to her something which she can understand. She has not gone to school, she has not studied beyond 2nd grade. Okay, that's the thing.
This was 90, which year?
This is when I was a student in Loyola College.
That was 90.
That means 1957.
She was living there.
Yes, she was just 4 houses away from us. Okay. And then they were family friends in some sense. She had to make a poor living. She was, then it will take us far away from the topic. As a family friend, why, how we came to know each other, etc., that I will tell you separately. But it is, each year I used to go there. And even now you have a little slab saying this is where Ramanujan lived, etc., in Triplicane. If you go to Triplicane, and then I used to take any mathematician, German or Italian or whatever it is, whichever mathematician came for an Indian conference, I used to take them to their house. And then she is just living with memories of Ramanujan. Not that she became a widow at a very young age, and she was very orthodox. So there's nothing like compromising or anything. That's the kind of person she was. Now, this one is the first one which appealed to me on Ramanujan's work, the squaring the circle. So you are given a circle, and you want to construct by geometry construction a square whose area is equal to circle. We know that we cannot do it because pi being transcendental, you cannot do that. But Ramanujan's ingenious approximation is this one. So what he does is, you take the line AB as the diameter of the circle, and then you draw all these lines, OG, CF, CD, BE, AE, AL, LB, BK. Now LK, and then I have given you the instruction as to what are their various lengths. And the ingenious point is to finally come to the number 355 over 113 is his approximation to pi. And this is accurate up to 8 decimals. And I have seen several other papers which says the best
fractional choice with numerator and denominator, maintaining such high level of accuracy is 355 over 113.
130.
113, 113. Now, when you look at 355 over 113, it's a combination. Can you push it up a little bit up? Yeah. Okay. You get into numbers like 5 over 36 d square, where d is the diameter, 13 over 36, 13. So from 13 over 144. So then that's how you get 113 over 144. And I have the following proof. It is a formal proof which you can go through to check that the final answer, the constructed number is, can you push it down, the picture? And yeah, the bn square is 355 over 113 r square. Okay. And what he says is, in his modest way, if I take a circle of radius 40 miles, you have to think of a circle of radius 40 miles and draw by his construction. And by his construction, you get the square. And his assertion is the difference between the area of the circle and the area of the square is less than, absolute value is less than 1.5 square inches.
My goodness.
Yes, that was his first thing. Can you push the next one? Date of birth, yeah. Ramanujan was always attracted towards this kind of, what do you call them? I can't even remember the name. Latin square, okay? So this is, yesterday there was one girl, yeah. Can you raise up, please? She came, and then I asked her just for curiosity, what is your date of birth? She gave 5th August. Now, oh, this is not hers. This is mine. I'm sorry. I'm sorry. This is mine. 5th August 1940. So, date, month, the century, and year. You try to write it down, this 4x4 matrix. Okay? Then all you now notice is on the top, that is the algorithm. That is the algorithm. And then that algorithm gives you every row sum is the same, every column sum is the same, this 4 corner sum is the same, every something inside is the same, etc. This was one of his little curious thing. Okay? So, in fact, in those days, I used to be attracted towards 9x9 or 11x11 block with the numbers from 1 to, say, 1 to 81. Write it in such a way that each row sum, each column sum, etc. I took a photo of that, but unfortunately it is, I don't have it here. Okay, I wish I could show that. So this is normally an appealing thing for many people. So you can try, you can take the top matrix, keep the top matrix or take a photo of it. And then you go home and write down for your own things and be satisfied that that's what it is. Basically, the sum is the same. That's nothing special. But this was the thing which he used to think about many of such problems. Second. The third one, I don't want to take any more than 2 more minutes. Yeah. Okay. Now I asked my son to prepare this one. Yeah. Go up. Yes. Now, when you take the function fx equals x power k, the first derivative is kx power k minus 1. Repeating this gives more general result. D power a, dx power a, x power k is k factorial over k minus a factorial x power k minus a. So, Ramanujan was the very earliest person in those days to think of not just differentiation in integers, but in fractions. So can you push it up? Okay. So he wrote down d power half, dx power half x as gamma 1 plus 1 over gamma 1 minus half plus 1, x power 1 minus half, etc., etc. So then you need to check that it has a property, differentiate one more time, you get 1. Okay? At least when he did it, this is all the thing which I know. But what Ramanujan knew from this one was to write down on the left side an infinite series involving Bernoulli numbers, etc. On the other side, a continued fraction. God alone knows how he knew and how he wrote it. We have no way of knowing those things. But only thing is, he was a true inspiration for every mathematician in India. One of the mathematicians, I don't want to mention his name, he slightly complained once Ramanujan's work is not all that serious. And Professor Harish Chandra got really mad at the whole thing. He said, you have no business to talk about this great genius. Very rarely such geniuses are born. And there are very, many poor people who are quite brilliant in India. For all of them, he's the inspiration. Let us hope Ramanujan's Day inspires every one of you to be involved in mathematics and with no expectation. With no expectation. And that's all I would like to say. But whenever I talk about Ramanujan, I'm emotional. Thank you.
Now, I wholeheartedly thank Professor Raghavan for that extraordinary address on Ramanujan's brilliance. It was both enlightening and inspiring. Now, I request convener Dr. K. Manjunath Prasad to escort the dignitaries to the dais. We gather today to honor the illustrious Dr. T.E.S. Raghavan, Emeritus Professor in the Department of Mathematics, University of Illinois, Chicago. Now I request Ms. Aishwarya Nayak, Research Scholar, to introduce Professor Raghavan to the gathering.
Tiruvannamalai Echambadi Srinivasa Raghavan, one of the leading game theorists of our time, was born on August 5, 1940. He holds the degree of MSc in Statistics from Presidency College, Madras University, and received his PhD in Mathematics and Statistics from ISI Calcutta in 1968 under the guidance of legendary statistician Professor Kalyampudi Radhakrishna Rao. Professor Raghavan's interests are game theory, linear and nonlinear programming, matrix theory, applied statistics, operation research. Professor Raghavan has made many fundamental contributions to the field of game theory and equilibrium computations. He is well known for his contributions to game theory, decision science, and special matrices, and particularly to the topics on stochastic games and cooperative games. He has published more than 60 research papers, written 4 monographs, and guided 14 students. Being an ardent fan of Carnatic music, he has been organizing Chicago Tyagaraja Utsavam every year in Chicago. Following the ancient Indian educational system, he has been running a Gurukulam in game theory in his native Pulavanur, Tamil Nadu. In 2021, 2023, and 2024, the Gurukulam was organized by Iwsmga Manipal. He is also involved in organizing several other workshops and conferences organized by KRMs. He is currently with the University of Illinois, Chicago, and has held many visiting positions. Kerams Mahe is pleased to dedicate ICOTS 2025 to him on the occasion of his 85th birthday.
It is my pleasure to request Dr. Stephen J. Kirkland and Dr. K. Manjunatha Prasad to kindly come forward and present traditional honor to Dr. T.S. Raghavan. Today, we celebrate distinguished Professor S.K. Jain, a contemporary of Dr. T.S. Raghavan, who dedicated nearly 4 decades to Ohio University's mathematics department and led its Center for Ring Theory and Applications. Renowned for expertise in non-commutative rings, modules, and linear algebra, he published over 135 articles in prestigious outlets like Transactions of American Mathematical Society, Journal of Algebra, and Siam journals, while co-authoring key texts including Basic Abstract Algebra and Cyclic Modules and the Structure of Rings. He mentored 23 PhD students, edited 7 volumes on ring theory plus mathematics in ancient Jaina literature, earned the 1999 Outstanding Graduate Faculty Award, Fulbright Awards, and grants from NSF, DIAD, and UN, and held visiting roles at UC campuses, University of Chicago, IITs, and others, now advising at King Abdul Aziz University. As executive editor for Journal of Algebra and its Applications and a lifelong member of the Indian and American Mathematical Societies, his global lectures and conferences have shaped the field. We are delighted to honor Professor S.K. Jain at this time. I invite Dr. Samir K. Niyoti and Dr. K. Manjunatha Prasad to step forward and present this traditional honor to him.
I'm truly honored and highly cannot have words to speak how much all of you are doing for this. I don't think I deserve that much what you are doing. Thank you very much. I appreciate it. Okay, so last me for next 4 days. Thank you very much. Manjunathan and everyone.
In this moment, it is our honor to recognize the invaluable contributions of the invited speakers and resource persons who have enriched the International Conference on Linear Algebra and its applications with their expertise and insight. Their dedication to advancing research, fostering collaboration, and mentoring young scholars truly reflects the spirit of this conference. It is my pleasure to invite Dr. Stephen J. Kirkland to come forward and honor our esteemed delegates. To begin with, we have Dr. N. Igambaram.
Is that the better place? Aishwarya, is that the better place? So that people can get up? Yes. Yes. Sorry, Kamaram. You know. Yeah. No, it is fine. Yeah.
Dr. Kuncham Shyamprasad. Dr. Sachindranath Jayaraman. Dr. Bojan Mohar. Dr. Balaji Ramamurthy. Dr. Kedukodi Babushri Srinivas. Dr. Mika Matila. Dr. P. Sam Johnson. Rajesh Kanan M. Dr. Debajit Kalita. Thank you, Dr. Stephen J. Kirkland, for presenting these honors. Before we continue, I would like to take a moment to express our sincere appreciation to a few of our distinguished speakers who, due to prior commitments, were unable to stay with us until this point in the program. Though they are not present right now, we truly value the time, insight, and expertise they shared earlier in this event. At this point in our program, we would like to invite any participants who wish to share their thoughts, reflections, or suggestions about the sessions, discussions, or overall experience so far. We would truly appreciate hearing from you.
there is
Come, somebody should come and speak about Manjunathan also.
your life is
Yeah, wait. He has worked so hard.
I see.
Yes.
Those who
Yeah. Please, let me give. I am Yagambram, retired from Indian Statistical Service as Deputy Director General. I took my PhD from Indian Statistical Institute in the year 1989. Though I was in the service, Indian Statistical Service, I had interest in research and teaching because I started my career as a lecturer at Annamalai University. I had great respect and regard about Indian Statistical Institute. So after joining the service, I joined as a research scholar at the Indian Statistical Institute, Delhi. And that interest continued till my retirement and after my retirement. In true recognition of my spirit for research, Professor Buffett used to encourage me, and we used to discuss many problems in matrix algebra. And through Buffett, so I was introduced to Professor Manjunath. Manjunath took interest in me, and he used to invite me to all these conferences. It was my privilege to participate as invited speaker in all these conferences. Even now that the interest continues. The way Professor Manjunath organized these conferences, it is really wonderful. You cannot find any flaw in the arrangement. In the Manipal University, especially, he has done a wonderful job. It is all because of his enthusiasm, his real interest in research, and that has made him organize this periodically. And I really wonder such personality. And here, after coming here, have been given all the facilities necessary for me to participate, to give my talk. And really, it was a wonderful experience. And this spirit will continue. And he will continue to encourage me in future also, I hope. And with this spirit in mind, I have nothing else to say. The spirit for research, the spirit for truth, the spirit for analysis, the spirit for understanding life. Because the understanding life is the main thing. And this mathematical research or statistical research, they are all only instruments. Just as a computer or other devices are used for analyzing further, these devices of mathematics or statistics now should be used for understanding what is life, what is me, what is the self, what is this, what is life. And that sort of research will leave you to wonder, who am I? What is this? What is this? So what is this? This has happened well, everything happened well.
because of Professor Manjunath. I thank you. I appreciate him on this occasion. Thank you for giving this opportunity to express my thanks and gratitude to you. Thank you.
Thank you, sir. I now request any of the participants or contributory speakers to come forward and give their feedback.
Eminent professors, mathematicians, all the participants, good morning, one and all. I am very happy to share my feelings on this platform. First of all, I express my sincere thanks to Professor Manjunath Prasad and his team for organizing such a beautiful event. As an administrator, I know how much difficult organizing a event of this type. I have been attending for the ICLA since 2014. I attended in 2014, 2017, now 2025. I have been observing, I have been learning many things from these conferences. I have been learning, and it is actually a good platform for youngsters to get exposure to the recent trends in mathematics. It's really helpful, sir. Thank you so much for conducting this type of programs. This time also we enjoyed accommodation, food, everything is very nice. Thank you so much, sir.
Thank you, sir.
Good morning to all. So on behalf of all the participants, I would like to thank Professor Manjunath Prasad for organizing this wonderful event. Organizing an international conference, it's not easy. So every one of us knows this very well. And this is the 6th edition. He has successfully conducted a conference on a particular theme. So having invited experts in this domain and especially giving opportunity to the research scholars to present their research papers. So if you look at the participants of this generation, maybe after 5 years, 10 years, so then they will be in a different places, different institutes, where you may realize that we have attended this conference together. So definitely you will notice, because on a one particular domain, this has been organized very well. So I would like to request all the participants to give a good round of applause to Professor Manjunath. So thank you.
Thank you, sir. Your feedback is invaluable and it helps us grow. We truly appreciate your participation. We now request all the participants to proceed to the ground floor for high tea. The technical sessions will begin shortly after the tea break. Thank you.
Okay, just one sentence from my side, because I may not spend too much of time to offer my time at the end. Like, so many of you might leave by the
Mike.
Probably I'm audible to everyone.
Yes, sir.
Okay. Just one sentence. If at all you find that this ICLA series is successful, it is because of team led by Professor Bapat, Professor Iclaa, and Simon Puntanan. And here, these myself, including myself, we were forming a scientific advisory committee. Then organizing team over here, they were behind us, behind this scientific advisory committee, and brought this particular series to this level. So all thanks goes to them. Yeah.
Yes.
Yes, yes. I'll come with the highest side with this.
You want that?
Oh, right, yes.
So I don't have to go to the road market to buy more. Yesterday we went to buy some.
What are you going to do? I don't know what to do. What you can carry, no? Huh? Now it may be time. You can have your cup of tea.
A cup of tea and then rush.
He started his teaching career in That is not good, sir.
In Becca.
It is better to conduct the institute only.
Cover.
But since we have a
Ah.
department, they will have to
French and ಅಲ್ಲಿ ಆ room ಅಲ್ಲಿ ಇದೆಯಾ ಅಂತ. Very short.
you had one direction.
No, you're proof.
No, I said it. Yesterday we looked at
আমি দেখতে পাচ্ছি
Yeah. You can have tea. Now is the time to.
Actually, because of the medical staff, they are. Five zero. Not one five.
No, I was wondering. How come you are running?
Okay, I was going to 10:50. Then 50. There are 4 speakers. Do you wish to introduce them?
Okay, we are in time.
So yeah, yeah, you can call them with the special. Or if you wish, you can. Somebody sitting here. I'm not. Somebody will be sitting here. I'm not, because I can keep my tag. You keep it. I can keep it here. Yeah, safe enough. Yeah, it's safe. My laptop is here. This is. Well, no problem. Thank you. Be here. Yeah.
Whatever government policy of calculate those and the draft of in the context of those schedules. So they are being inspired by what no need for it okay, on it, there, by, what is, it was all, that cover all by, okay, we have, like, what I must, for that, must have some. Or, like, calculation. Presentation prepare able to find it and you want to follow and all is the other time. Want to both of them, like whatever plan is like, that also 78 years. Because that's how we have solved all the in more time, like when you have an idea that more is you can't go very well, but any more is well. So not LPP can be solved by simple method. Or try simple method, simple method, Python, simple method, method. So each simple method was different technique. So you can't solve all the LPP by simple. Okay, some of the most I think solve it. When equality, if you get another you can pay as the answer, it's done. So we will forget by another to take it. Like that, we have if all the very. So how can we solve a larger support of before the you told them. If I don't include money, you say if I any kind of add something that you don't know. I already something that right, if they go to the river, so I have not our original is easily well or if the quota is the quota if we are in the the contract is all in law of that. Okay, generally, get of the foundation is but is connected if there is don't get it if we don't have if we don't have derivative, we don't have no. Something like that. Hello, sir. Hello, sir. But
As you were scheduled. 10:50, you were supposed to, uh, no. My bag is lying here somewhere. My bag containing the fruits and short is here.
I've kept it in the pancake.
Pardon?
I've kept it in the pancake. And you're leaving?
Short is here. First thing you use that. Okay. Well, you know. The edge, the right edge. The body should be floating for father. Oh, G, not H. Pala G, Pala. Right. Right. I don't know. Yeah, I know. Labor, not labor, 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 right.
Yeah, after you.
Thank you so much.
Then, okay. Then,
welcome everyone. We'll begin the session now. This session is chaired by SK Jain sir. So over to you.
Welcome everybody to the next section coming. The first speaker is Balajit Ramamurthy from IIT Madras. He is speaking on some connected graphs.
Let me introduce the speaker. Dr. Ramamurthy is a professor in Department in Mathematics at Indian. Sorry, Dr. Balaji Ramamurthy is a professor in the Department of Mathematics at Indian Institute of Technology, Madras, India. His research focuses on complementarity problems on symmetric cones, spectral properties of non-negative matrices and their generalization. With several research papers published in reputed national and international journals on linear algebra, optimization, complementarity problems, and distance matrices, he has made notable contributions to these fields. Let's welcome Dr. Balaji Ramamurthy.
This one.
Over to you, sir.
Okay, thank you very much. So I come from IIT Madras. So what I want to talk is on these distance Laplacian matrices. So let me come straight away to this one. Suppose you have a connected graph on n vertices. Associate some matrix to this graph G. Usually you take adjacency matrix, Laplacian matrix, etc. There are some other matrices also, say normalized Laplacian matrix, distance matrix, maybe some other matrices also, I don't remember. Eigenvalues of this matrix may give some information about the structure of this graph. So can you deduce some result about the graph using the spectrum of the matrix that you have already associated? This is the spectral graph theory, which you call. A typical result in this spectral graph theory, let A be the adjacency matrix of a graph G. G is bipartite if and only if whenever lambda is an eigenvalue of A with multiplicity M, then minus lambda is also an eigenvalue of A with the same multiplicity. Yesterday I learned from Professor Mohan that G is bipartite if and only if it is spectrally symmetric. That word I am not aware, so anyway, it's already you have heard about this one. This is a typical spectral graph theory result. Other matrix, Laplacian matrix. Just let me recall the definition of this Laplacian matrix. Take the adjacency matrix and then construct a diagonal matrix with degrees on the diagonal, and then subtract these two matrices. You get the matrix which is called Laplacian matrix. There are other ways of defining this Laplacian matrix also, but anyway, this is more elementary. So consider this a cycle 1, 2, 3, 4, 5. Laplacian will be -1, 0, 0 because 1 is adjacent to 2, 1 is not adjacent to 3, 1 is not adjacent to 4, whereas 1 is adjacent to 5. And then calculate the degree of the first vertex, it is 2, and construct the matrix like this. So this is the Laplacian matrix L. Important point is that if you take the row sums of L, it is 0, column sums of L is it is 0. So L acting on a vector 1, 1, 1, 1, 1 will be 0. So okay, so let me start with the result, which is proved by one of the all-time great Fiedler in I don't know whether I wrote this year correctly or not, 1973. You can check in the internet. This is one of the basic result in this field. Take a connected graph on n vertices, construct the Laplacian matrix, First smallest eigenvalue is of course 0 because I told you that determinant is 0 and L is a positive semi-definite matrix. So go to the second smallest eigenvalue, it is a positive number. Take the eigenvector corresponding to this second smallest eigenvalue. Take any eigenvector. Okay. And then you construct two sets. Xj such that where the component xj's are non-negative, that is that you call it as x, and y collect all the components of xj's which are negative. Okay, so there is a y. So in this way, I'm going to partition this set 1, 2 up to n. Okay, x union y will be 1, 2, 3 up to n. So his theorem, of course, x and y are non-empty. That will come immediately. It's not a no technicality involved here. But Fiedler showed that subgraphs induced by x is a connected component of G. Subgraph induced by y is also a connected component of G. So this is the result proved by this one. So this is called a Fiedler partition. And just to illustrate this result, consider this example. It's a unicyclic graph. There is a triangle, and then 3 is connected to 4, 4 is connected to 5. It's a connected graph on 5 vertices. I have written the Laplacian here. L is this 5 by 5 matrix. It's a positive semi-definite matrix with the rank 4. Fiedler vector I computed and it's approximately 0.5, 0.5, 0.1, minus 0.4, minus 0.7. So my x will be 1, 2, 3, where the components are all positive, and y will be 4, 5, which are the negative components. So find the induced subgraph, find the subgraph induced by the set x. Also find the subgraph induced by the set y. So I have written the subgraphs induced by x and y. This is a triangle 1, 2, 3. Subgraph induced by y is 4, 5. So both these graphs are connected. So this is just a small illustration to this Fiedler's result. What I thought was, okay, so this is a very famous theorem in this field. Instead of adjacency and Laplacian matrix, can we associate some other matrix, and whether this spectrum of this matrix will give you some information about the graph? That's what I was trying to look at it. So what my aim is just to take the distance matrix of G first, and then you define the distance Laplacian matrix. Anyway, in the sequel, let me show that these eigenvalues of this distance Laplacian matrix may give some information. Distance matrix, how to define a distance matrix? Take a connected graph, compute this shortest distance between the two vertices, I and j, and then write the distance matrix. Diagonal entries are going to be zeros, and D12 means it is the shortest distance between 1 and 2. That is the length of the path that connects 1 and 2, and this length should be the shortest. This is the way how you compute D12, and then you form this distance matrix where the ijth entry is Dij. Just a small example to illustrate this one. Take this connected graph, and then if you see 1 and 2, 1 and 2 are adjacent, so 1, 2th entry is 1. Suppose you go to 1 and 4, the shortest, is it correct? No, wrong. Okay, correct. 1 and 2, 1 and 4 is 2, and 1 and 5 is 3. Okay, 1 and 5 is 3. So in this way, you construct this distance matrix. Okay, now let me define what is called this distance Laplacian matrix. Instead of adjacency matrix, consider this distance matrix, and then take the diagonal matrix where the diagonal entries are going to be the row sums of this distance matrix. So diagonal of first entry is the sum of all the entries in the first row of D, that is sigma over j, D1j. Second entry is second row sum. Third entry is a third row sum, and so on. Okay, this is the distance Laplacian matrix. So I have assigned the notation L tilde here. And L tilde for this matrix for the graph which I have shown is I have written here 7 minus 1 minus 1 minus 2 minus 3 and so on. See, the point is that in a Laplacian matrix you can have 0 entries in the off diagonal. Suppose the any two vertices are not adjacent. Suppose I and j are not adjacent, then you will be having ijth entry will be 0 in the Laplacian matrix. Whereas if in this L tilde, you can say that all entries are going to be negative in the object. So that is a main difference here, and this difference creates a lot of difficulties in this one. So, say I'm not the first person to consider these kind of matrices. Some paper I saw in 2013. There was a paper on this distance Laplacian matrices, and also they obtained the one non-trivial result. At least I thought I will say this is a theorem obtained in 2013 by I don't know, I don't remember the name. Hansen somebody. So they proved this one. Suppose you have a connected graph on n vertices, and if you take the second smallest eigenvalue of the distance Laplacian matrix of G, then lambda is greater than or equal to n. And the equality holds if and only if the complement of G is disconnected. That's what they proved. Okay, my interest is to get a theorem which is analogous to the Fiedler's theorem for distance Laplacian matrices. What we did was we did some computations. From those computations, we observed the following. Suppose you take a connected graph on n vertices. Suppose lambda is the largest eigenvalue of its distance Laplacian matrix. In other words, lambda is the spectral radius of the distance Laplacian matrix. And you consider any eigenvector associated with lambda. Then you partition the set 1 to n like this. X equal to j such that xj is greater than or equal to 0. You define y to collect all the components where xj is negative. Then the induced subgraphs are connected. So that's the observation that we made from those computations. And this result is known for paths. For the path, Professor Bapat gave a proof. He did not publish, I think. He has put it in his. I saw in the internet some notes he wrote, and still I think it's available in the internet. Using direct computations, he shows this one for paths. But I asked my student to show it for any general tree, and of course he came up with a proof also. So this is a theorem which is proved by my student, and also I'm also one of the authors, I think. Take a tree on n vertices. Suppose L tilde is a distance Laplacian matrix of T, and if X is an eigenvector corresponding to the largest eigenvalue of the distance Laplacian, then the subgraphs induced by the positive and the non-positive coordinates X are again trees, or otherwise they are connected subgraphs. So this is the result, and of course the proof involves some sort of a technicality. You have to use the technique of the Fiedler, but also you have to do some more calculations that involve some identities between distance matrix and then the Laplacian matrix, and you have to manipulate something. Finally, you get a proof. This is one of the main theorems that we want to say today. Just to illustrate this, consider this a tree. Consider this tree 1, 2, 3, 4, 5. This is not a path. Okay, it's not a path. Take the distance Laplacian matrix. This is the distance Laplacian matrix. Eigenvector corresponding to the largest eigenvalue. It's a 5 by 5 matrix. So there are 5 components are there. First 3 components are negative. Last 2 components are going to be positive. The induced subgraphs are 1, 2, 3, 3 and 4. Of course, they are paths, so they are trees. It's a small illustration to our result. Okay, so this is a. No, are you all right? What? Okay, coffee. Can get okay. Okay, fine. So this is the first result, and let me move on to what are called threshold graphs. Threshold graph is constructed iteratively by adding an isolated vertex or a dominant vertex. Dominant vertex means add a vertex and then connect this vertex to all the previous other vertices. That is a dominant vertex. Isolated means just it's isolated and do not connect it to any other vertex. Graphs constructed in this way, they are called threshold graphs. There are many characterizations of these threshold graphs. One characterization usually people consider is the graph is threshold if and only if you take any induced subgraph with the 4 vertices, then it cannot be the path on 4 vertices or a cycle on 4 vertices, or it cannot be 2k2. Okay, so this is a characterization of threshold graphs. Even you can take it this as a definition of a threshold graph. So this is a threshold graph here. Okay, so this is an example of a threshold graph, but this is not connected. The following theorem characterizes threshold graphs. It is observed by Meris. Suppose you take a connected graph with adjacency matrix A and a Laplacian matrix L. Now you form a new matrix A down arrow like this. You take the first row, for example, and then rearrange the entries in the non-increasing order. That is a decreasing order. First largest, then the second largest, and so on. Graph is a threshold if and only if the eigenvalues of L are the column sums of A down arrow. So that's the theorem. This theorem can be stated in combinatorial language also, but for now, this is more convenient here. Just you consider this graph. This is a threshold graph. It doesn't contain any, if you take any 4 subgraph with 4 vertices, then the induced subgraphs are not path or cycle or 2k2. So it is a threshold graph. Construct the adjacency matrix here. Okay, 0, 0, 1, 0. For example, just to take the first row alone, 0, 0, 1, 0, 1. If you arrange in the non-increasing way, it will be 1, 1, 0, 0. So like that, you do it for every row and then calculate the column sums. It will be 5, 4, 2, 1, 0. So this is the eigenvalues of the Laplacian matrix, 5, 4, 2, 1, 0. So threshold graphs have integral Laplacian eigenvalues. And this theorem characterizes threshold graphs. Can we characterize distance Laplace, not distance Laplace matrix, threshold graphs, I wrote it wrongly. Can we characterize threshold graphs through the spectrum of distance Laplacian matrices? Through examples, we noted that the same kind of Meris result holds for distance Laplacian matrices too. Okay. So this is a result with my students. Suppose G is a connected graph with the distance matrix D and distance Laplacian matrix LD. We form a D down arrow be obtained from D by rearranging the entries of rows of D in a non-increasing order. Then G is threshold if and only if the eigenvalues of LD are the column sums of the matrix D down arrow. So this is a main result which characterizes threshold graphs through this distance Laplacian matrices. Suppose just to come to this example here, consider this threshold graph. I have written the distance matrix D here, and then rearrange the rows of D to form this matrix 2, 2, 1, 1, 0, and then compute the column sums. It is 9, 8, 6, 5, 0, and 9, 8, 6, 5, 0 are the eigenvalues of the distance Laplacian matrix LD 9, 8, 6, 5, 0, and so this is another result that I want to state about this distance Laplacian matrix. Okay, let me come to the final part here. Of course, this is not a spectral graph theory. Maybe you can tell that it's a combinatorial matrix theory result about a distance Laplacian matrix. Okay, first let me have to tell you what is a Moore-Penrose inverse. Suppose the determinant of a square matrix is 0, then you know that A has no inverse, but there is a unique matrix X that satisfies all these 4 conditions: AX A equal to A, X A X equal to X. AX and XA both are symmetric matrices. This matrix X is unique, and the name given is Moore-Penrose inverse of A. Symmetric case, you need not worry. Just take the spectral resolution of A, U, and then a diagonal matrix U transpose, then the Moore-Penrose inverse will be take the reciprocal of this non-zero diagonal entries, and then you will get the Moore-Penrose inverse of A. So this is the, okay, now let me come to the problem here. Take a connected graph on n vertices and write its Laplacian matrix L of G and define a vector 1. 1 is equal to 1, 1, 1. So L of G acting on 1 is 0 because row sums and column sums of the Laplacians are 0. Now you take the Moore-Penrose inverse of L of G. Okay, so it is denoted by L of G dagger. A question that arises in applications is find G such that all off-diagonal entries in the Moore-Penrose inverse of L of G are not positive. Such graphs are very difficult to construct. Complete graphs satisfy this property. That's only a classroom exercise. Among trees, only star satisfies this property. So I have written Kirkland and Nyman, and I think it's correct. Okay. So only star satisfies this property. So no other tree will have this property. Okay, now let me come to the distance Laplacian matrix here. LD of G acting on 1 is 0. So determinant of LD of G is 0. In view of several computations, we know the following remarkable property. If G is a connected graph, then all the entries in the Moore-Penrose inverse of LD of G are non-positive. Of course, I am not the first person to note this one. Michael Neumann, I heard that he noted this one. But anyway, so I have no reference for this one. So what is the proof of this result? I don't have any proof for a connected graph, but we can show it for a tree. Let a T be a tree, then all the off-diagonal entries in the Moore-Penrose inverse of its distance Laplacian matrix are going to be non-positive. So that's a result which we got for trees. Just let me example to illustrate. Consider this a tree 1, 2, 3, 4, 5. Distance Laplacian matrix, I have written this one 5 by 5. Moore-Penrose inverse is Z matrix. This is the thing that I want to say about distance Laplacian matrix. Of course, I think many more things can be done. Anyway, I'm not an expert. My student is an expert. So, yes. Okay, some of the references I want to show here. I think this is already published in linear and multilinear algebra. I have to ask Gargi whether it's already published or not. Gargi, myself, and then my student Vinayak. And okay, so Maris has written a beautiful paper, Degree Maximal Graphs are Laplacian Integral, year 1994. Okay, so this is the thing I want to say. Thank you very much.
Any questions, please?
You want to ask?
Thanks. So I'm just looking at your plan of trying to develop a Fiedler theory for the largest eigenvalue of the distance Laplacian. Do you know examples where that eigenvalue has high multiplicity?
With multiplicity more than 1.
Yes.
Largest eigenvalue.
Mm-hmm.
I think it's possible.
You think it's possible?
It's possible, I think, but
of course.
have to see.
Yeah, right. Okay, Boyan says Kn, of course.
It's possible, right?
But complete graph is then the same, right?
Right.
Yeah, it's possible.
Yeah, so I'm just curious in that sense because then
A complete graph, it's the same. Distance Laplacian. Yeah.
right. So in that case, you've got lots of different choices for the eigenvector that's associated with the large eigenvalue. Do you see anything interesting about the structures in those cases?
No. But our theorem, so far we have proved only for trees. And for trees, you may guess why we have proved for trees. Distance matrix, it can be written in terms of Laplacian. Dij equal to Lia plus. So that expression is more in the proof technique. That expression plays a more important role. Whereas for a connected graph, Dij is horrible because distance matrix is no longer an Euclidean distance matrix. We cannot do much in this one. So.
Thank you.
Any other question? Nor we thank the speaker for a very nice talk. The next talk will be, let's go in minutes then. It is 11:46 minutes. It's faster. It's okay. Hey, you did a good job. Next talk will be 6 minutes. No, more than 6. 11.
You can start now.
11:25. 11:25. So 1 hour is what? 50. So we can start now.
I think you can start now, so.
What you said, I mean, he's a coordinator, I asked him. Maybe some people are waiting. People are waiting, they'll come only 11:25. So we cannot start early. We cannot start early. According to what it says.
The whole is supposed to be there.
It's supposed to be.
Okay.
No more coffee available, they can go and downstairs get a coffee. Technically, it's not there, not there, no. Drink some water. Yeah.
Already can say something more.
Keep it up, go fight, eh? Keep us up.
Already.
So come. Pardon.
So come.
Oh, pardon. Some more questions.
Some more questions.
No, I cannot answer.
So you, something that.
My time is over.
IIT Madras, so that they are working on university. Right? So that's your point. So this is one way that one can construct university.
Yes, this is somewhat combinatorial problem. More complicated.
So,
Start multiplying matrices.
by the way, can you look at this one, that classes of graphs, for which it is instead of T, it is hidden.
Yeah, this uses the graph structure.
So this D matrix is a subclass of identity, but non-trivial.
But the Laplacian matrices are in Z matrices. So that's why same sign pattern you want.
But it is a nice way you have explained.
Yo.
Without much this one, no, that getting
I
it
am-
complicated.
I am. So what we. There are a lot of papers in the editor and graph. There some of them do not get good. Why everything? But in your case, I think I do find some motivation.
Oh, thank you.
Yes, okay. I do find this is motivation. Otherwise, I was, who are the one who takes this graph? Be careful.
I believe that there could be some activities network activities.
Anything.
Many people that those business people are doing. Your MBA department. Management department.
I was there writing my drafts, man. Okay, that's.
Yeah.
You were there,
Yeah,
right?
yeah. Max department.
Okay. Yeah, I very confident. In my department.
He is a young person.
Yeah.
So you want.
I don't know.
How old do you think he wrote that?
He is spontaneity.
Started now, I think, 7:19. Okay.
So he is working in Stanford.
So here's a good table. Somebody if you put the partition work. It's after you never get and let's you can start because. Yeah, that is until the heading and. Well, okay, yes, everybody wants to start, we can start. The next speaker is Dearjit Kalika from Assam. Kalika from Assam.
Let me introduce the speaker. Dr. Debajit Kalita is an associate professor in Department of Mathematical Sciences in Tezpur University, India. He received his MSc from Guwahati University and PhD from IIT Guwahati. His research focuses on algebra graph theory, linear algebra and its application to graph theory, and adjacency and Laplacian spectra of graphs. He has published several papers in the area of graph theory. Let's welcome Dr. Debajit Kalita. Over to you, sir.
Thank you. Good morning, everyone. So there is a property of graph called SR property, means a strong reciprocal eigenvalue property. What it is, we have a graph, we have the adjacency matrix. If lambda is an eigenvalue of the adjacency matrix, 1 by lambda is also an eigenvalue of the matrix with the same multiple. And this was started by Barik and others. And they proved that the trees having that property, they are all corona trees. Corona trees means we have a tree, we add vertices with a single edge to all other vertices. The resulting is a corona tree. So any tree like that is called a corona tree.
So it came with the coronavirus?
No. Maybe because of the corona tree, coronavirus has come. Then again, Barik and others, they characterize those unicyclic graphs for which that type of property holds. And they prove that those unicyclic graphs, which are bipartite, and their guard is not equal to 4, they are corona unicyclic graph. Means you have a unicyclic graph, you add edges to all the vertices. And when the guard is not equal to 4, then they have also characterized those, and they are those are the non-corona unicyclic graphs. And here we will try to find the bicyclic graphs. And again, here we interestingly see that if the bicyclic graph do not contain cycle of length 4 and it is bipartite, then that type of property holds only for corona type of bicyclic graphs. And when
So there are different variants. Different variants, they have a family.
yeah. So when the bicyclic graph do not contain any cycle of length 4, then the corona bicyclic graphs will have that property. And when the bicyclic graphs contain cycle of length 4, we will have some other. Now, I don't know why this cycle of length 4 is creating. It is interestingly because for unicyclic graphs, where you don't have a cycle of length 4 in that graph, then we are having corona unicyclic graph. In bicyclic graphs also we are having that if it has no cycle of length 4,
Then again, that type of property holds only for those bicyclic graphs who are bipartite and they are corona. And there are also bicyclic graphs where it contains a cycle of length for having that property. Now, in order to get that, we study those bicyclic graphs and their inverse. Inverse means that we have a graph Z, we have the adjacency matrix. If it is non-singular, so we have the inverse of the matrix. And the graph associated with the inverse of the adjacency matrix, that we call as the inverse. And here we will take our class of graph to be bicyclic graph, because our intention is to find bicyclic graphs having SR property. So here is the definition of the adjacency matrix. All of you are aware of this almost. So Aij is 1 if there is a edge between I and Z, and otherwise it is 0. And we call the graph non-singular if adjacency matrix is non-singular. And the first definition of graph inverse was given by Harare and me in 1976. So they call a graph Z invertible if AZ inverse is a matrix with entries 0 and 1, just like the adjacency matrix. But with this definition, they can see that there is only one type of graph, K2. So it looked not very interesting for the researchers later. So then Gottschall came with a new notion of inverse. So what he called a connected graph Z to be non-singular if it is signature similar, if its inverse matrix is signature similar and to a non-negative matrix. So with this definition, there are a lot of research available. And the weighted graph with that as the adjacency matrix S, AZ inverse S, is called the inverse of the graphs, where S is a signature matrix. And with that, there are a lot of research available. So Akbori, Kirkland, Tiefenbach, Newman, Forti, Panda, they have done a lot of work. But then we see that there are also graphs. This is in particular. This is not invertible as per Gottschall's notion. So what we call then, because of that, a graph Z, we say Z is a non-singular graph. We call Z invertible if the diagonal entries of AZ inverse are all 0. That is the most natural, because then we can say that the AZ inverse is just behaves like adjacency matrix of a weighted graph. And the weighted graph associated with that type of AZ inverse, we denote it by this symbol Z plus. And we call this G plus to be the inverse of Z. Now, in particular, if the underlying graph of Z plus is isomorphic to the original graph Z, we call the graph Z to have a self-inverse, or simply it is a self-inverse. Now, there are some work that we did with my students for non-bipartite unicyclic graphs with unique perfect matching, and for having unicyclic kind of inverse, bicyclic kind of inverse, tricyclic kind of inverse. And then Osborne, they have studied sine invertible graphs. And in a recent work with my student, we have characterized bicyclic graphs for which B plus is a tree, unicyclic and bicyclic. And here we will identify those bicyclic graphs who are self-inverse.
Now there are two types of bicyclic graphs. This type were infinity type and theta type. They are likely something like this. And we all know what is a perfect matching. It is a spanning subgraph such that each component is an independent edge. And we call a path in a graph having unique perfect matching, alternating if the first edge and the last edge is a matching edge and others are alternatively matching, non-matching, something like that. And these are some notations that we will follow here. And what is a simple corona graph? So we take a graph Z and we add vertices with an edge to every other vertex. That type of a graph we call a corona graph. And if Z is a simple corona graph, then Z is always a self, Z has a self-inverse. So Z is self-inverse. So this is proved in 2007 by Ye and others. Now, first we will look at the bicyclic graphs without a four cycle. So say B is invertible and say B does not contain a four cycle, then B is self-inverse if and only B is a simple corona. That type of thing is true when we do not have a four cycle. So a non-corona bicyclic graph having a self-inverse must contain a cycle of length 4. And because of that, in the next few slides, we will consider bicyclic graphs having a 4 cycle. So this is if B is a bicyclic graph where B minus BU, that BU stands for those bicyclic graphs having unique perfect matching. Okay, then there is only one such bicyclic graph without a unique perfect matching but having a perfect matching, who is self-inverse. So because of that, next slide, so we will consider bicyclic graphs having unique perfect match. Now let us see what is a peg. Suppose we have a cycle gamma in a graph, an edge Ij, who is a matching edge, is called a peg if either it is a chord of gamma or exactly one of I or J is a vertex of the cycle. Okay. And a peg E is called external if E is a bridge, or otherwise we call it as an internal peg. Now let us see what is an AP5 path. So this will be crucial for our discussion. Suppose that we have a 4 cycle, say 1, 2, 3, 4, 1, that is the cycle. And we see that there can be 4 pegs for that cycle or 2 pegs, because we must have a unique perfect match. So it has 4 pegs, then all its edges are not part of any alternating path of length greater than 3. Whereas if it has 2 pegs, then we see that this we have that type of a structure. And when we have that type of a structure in the graph, this 1 dash 1, 2, 2 dash, these are 2 pegs. And the path 1 dash 1, 4, 3, 2, 2 dash, who is a path of length 5, and it is an alternating path. So this type of a path we call as AP5 path. We refer to this as AP5 path associated with that cycle gamma. And the pegs 1 dash 1, 2, 2 dash, we call them a null peg. We have given a name. And in the graph, if we have any other alternating path of length 5 apart from this type of a path, we call them as non-AP5 path. Now, what if B, a bicyclic graph, who do not have an AP5 path? Now, in that case, again, we see that it is a self-inverse if and only if it is a simple corona. Now, what if B has an AP5 there? Now, let us take B, a bicyclic graph with unique perfect matching who has an AP5. Then we have few things here. Suppose that B has an AP5 and it has, say, exactly one AP5 path. Then B plus is bicyclic if and only B contains exactly one non-AP5 path that passes through at most one null peg in society. So that means a non-AP5 path cannot pass through both the null pegs of a cycle. Now, if in particular B is an infinity type bicyclic graph and B has say two AP5 paths, then B plus is bicyclic if and only B contains two non-AP5 paths, both of which pass through again at most one null peg of the same cycle. So of the same cycle, these non-AP5 paths cannot pass through both the null pegs. This is the criteria. So based on these observations, these things, we have constructed all possible bicyclic graphs having self-inverse. Now let us define an operation which is known as a pasting. Suppose we have two graphs C and H, where x dash is a pendant edge, so it is obviously a matching edge, and y dash is another pending edge here. So by pasting x dash onto y dash, we mean this graph. We will just paste the edge x dash with y dash y by keeping x as y dash, x as y, x dash as y dash, and we get that new graph. So that new graph will be obtained by pasting Z and H like that. Now, let us call a tree palindromic, which we can construct like this. Suppose T is a simple corona tree on the vertices 1, 2 to n, and take a copy of T. So we call it T dash, and we label the vertices by 1 dash, 2 dash, and n. A palindromic tree is obtained from these two copies of T by performing the following operations. So take a vertex x of T, join T and T dash by adding an edge between x and s. Or take a pendant edge xy of T, paste xy of T onto x dash y dash of T dash, and then paste the pendant edge of a simple corona tree, something simple corona tree F onto the edge xy. And similar kind of thing we can do it for these two distinct edges also. And in that case we will obtain a palindromic unicyclic corona graph. So here is an example. You take this tree and we have obtained this new tree, which we call as palindromic tree, and we call these edges of the two copies, the green edges, they are called mirror edges. These two blue edges, we call them as mirror edges. And similarly, we get in another way a tree like this, which also will be a palindromic. So here F is a corona tree. Now we will find all those self-inverse bicyclic graphs who contains an AP5 path. Okay. And here our bicyclic graphs are of infinity type. We could not combine it for all. That's why we need to separate it infinity type separately, a theta type bicyclic graph separately. Then B is self-inverse if and only if B has either this type of a structure. Here we have T is a corona tree. We have pasted it 1, 1 dash. U is an unicyclic graph. We have pasted it 2, 2 dash unicyclic corona graph. We have pasted it 2, 2 dash X, X dash. And that same tree we have pasted at Z, Z dash. And same edge that we have pasted here in 1, 1 dash, we have pasted it in Z, Z dash. So this type of a bicyclic graph will be self-inverse. Or it will be like this. Again, here T is a corona tree. We have pasted it with U dash, 1, 1 dash, and U is a unicyclic corona graph. We have pasted it with 2, 2 dash. This here, there also U is unicyclic corona graph. And now what if it contains 2 AP5 paths? So it will be of this type, the structure. If it is bicyclic, if and only if its structure has to be like this, or there are many other structures will come. So again here that pasting kind of thing we have done. Here TP is palindromic tree that we have defined. Because of that purpose only we have defined the palindromic tree. TP is just a palindromic corona tree where T1, T2, these are any other corona tree. And we have pasted it like this and we obtained that structure. And this type of a bicyclic graph will have self-inverse. Or it has this type of a structure. Or it has this type of a structure. Here we see that these two are the non-AP5 paths. And there we have seen that these two are the non-AP5 paths that we must have. Or it has, if it has 2 AP5 paths, then B is self-inverse if and only structure of B will be of one of the following. So like this. So again here T1, T2, these are corona trees, and we have pasted there with pendant edges X, X dash, Z, Z dash, and R. Or it will have this type of a structure. So there are many structures that will come. We have did it with some combinatorial arguments. Or it will have this type of a structure. Or it will have this type of a structure. So here, this is one of the non-AP5 paths. And this is another non-AP5 path. This one. Now suppose that B contains 2 AP5 paths and the non-AP5 paths share edges with different cycles. Then B is self-inverse if B has one of the following structures. So this is one of the structures. So here this T is pasted at 5, 5 dash, 1, 1 dash. And T1, T2, they are pasted accordingly. Or it will have this type of a structure where TP is a palindromic corona tree. Or it will have this type of a structure. Now, this is the case when a pendant, a non-AP5 path share edges with both the cycles. Then we have this type of a structure. So here we have pasted and pendant edge of T with 1, 1 dash, and that same pendant edge is pasted there with another copy of T with U dash. Similarly, this one. So these are all having self-inverse bicyclic graphs. And then those are of infinity type. So now we go to the theta type unicyclic bicyclic graphs having bicyclic self-inverse. And first again we consider the bicyclic graphs with one AP5 path. Now if B contains exactly one AP5 path, then B is self-inverse if and only B has one of the four following structures. So this one or this one. Okay, here this path. This is actually not a path. This is connected by a palindromic simple corona tree. Although it looks like a path, it is. We pasted a palindromic simple corona tree at U dash 2 dash. And it will have either this structure or this. Now we have when theta type bicyclic graphs having two AP5 paths. So a lot of structures we have again. So it has two AP5 paths and B is self-inverse if and only we have this three and some more will come. So this. So these are all obtained with that pasting kind of a thing only. So those structures, if the bicyclic graphs having self-inverse will have all these lot of these structures. And again, as we have seen, graph Z is said to have a reciprocal eigen, and these are all self-inverse. And we will see that all these graphs, bicyclic graphs, will have this property, SR property. What is SR property? It is called strong reciprocal eigenvalue property. 1 by lambda and lambda, they are eigenvalues of the adjacency matrix with the same multiplicity. Now, as we have already discussed, this characterized by Barik, the corona trees and the unicyclic graphs. They have identified also the non-corona unicyclic graph with SR property. And now we will go to the. Now, when B is without 4 cycle, this B has SR property if and only B is bipartite and it is a simple corona graph. Now, if B has SR property, then B is invertible and B plus is a bicyclic graph that we have seen. And if B is self-inverse, we see that AB inverse is nothing but a -1, 0, 1 matrix. So it is kind of a mixed. We can see them as weights of 1 minus 1. And suppose B has self-inverse and B is bipartite, then B plus is going to be balanced. So the inverse is similar to the adjacency matrix. And because of that, we will have SR property because of that fact only. Now the question is, does there exist bicyclic graph that is not self-inverse but has SR property? The answer is yes. So we have now seen the non-corona bicyclic graph with this SR property. So this result characterizes all those bicyclic graphs having SR property. So either it will be bipartite and self-inverse, or it will have the following 4 structures. This one, this one, this one, and this one. And with this I will end. Thank you.
Very nice talk. Any questions, please? Any questions? Any questions?
We have some reference where you any modular was there some reference where you mentioned of unipolar matrices? No, maybe yeah, good for you. Okay. So here you consider only cycle 4, no?
I have considered all bicyclic graph,
All bicycling.
all bicyclic.
Okay, so if you have very large graphs, then how to recognize that such
Five views, we have worked on, we have
say
seen,
1,000 vertices are there.
yeah.
So that big, big one. So how you recognize? What is your recognition?
So in a bicyclic graph, we can either have one that non-AP5 part or two non-AP5 part. And so, uh, and we have AP5 part, at most two AP5 parts we can have. So studying those AP5, non-AP5 part, we have characterized those tasks.
So are you using this in some algorithms or
No algorithm.
or any applications? Are there? No application.
Any other question?
So these motivations are not from application. Only theoretical.
We have to, our motivation is to, we need to characterize the bicyclic graph.
It is certain nice theoretical features.
Yes.
Yes, I am always looking for motivation, but I think there must be someone here.
Yes. Because yesterday we have seen that there is a bipartite graph when the eigenvalues are symmetric. Because of that, people studied the graphs having this type of reciprocal type of property.
But what about those classes of graphs? It is not inverse is non-positive, but you mentioned about something, no? That in the beginning.
Inverse is
Non-positive.
is not similar to a non-positive metric.
Non-positive metric, but it's one of the submetrics, no? Say n-1 by n-1. So that is non-positive. So it breaks down in this one of the row. So such, what you can say about those kind of groups?
Those I have
You're not studied it. Somehow it is breaking down, no?
Okay, then let's thank the speaker. The next talk in 5 minutes, please. You have a speak question?
So just a comment, the question came out about motivation, and I think Chris Gotzel's original paper came from, was motivated by chemical graph theory, where they're looking at Huckel theory. The eigenvalues of the graph somehow represent energy levels for the electrons, and looking for bounds away from zero to ensure stability of the molecule. So I think that's the original motivation when people started looking at these things.
That history.
Yes.
Yeah, mathematical chemistry.
That's interesting. That's interesting. Okay, we'll be having the next talk in 5 minutes, please.
Nice to see you. See some techniques. Yeah.
And the point of view that now,
Open number.
I know that the US
No, it is. Yeah, I'm sure. I don't expect it. All right. Get rebuilt here. Yeah, that's it. What we love to talk about, Peter, glad, enjoy. He's gonna go anywhere. Yes. Most of that is my mind. No, one of them is only. Maybe. Right percent. Yeah. 3 minutes left on we should start. We can spend the minutes. All right, the speaker is ready and the audience is there. We can start with the next speaker. We can start with the next speaker, Professor Chaitanya Jai Raman from ICER in Tripura. Am I right?
Trivandrum.
Oh, Trivandrum. Okay, sorry. Correction. Trivandrum.
Let me introduce the speaker. Dr. Sachindranath Jayaraman is an associate professor in Department of Mathematics at IISER Tirunanthapuram, India. He earned his PhD and MSc from IIT Madras and MS from Texas A&M University, and previously served at IISER Kolkata and Chennai Mathematical Institute. His research focuses on linear algebra and matrix analysis. With numerous publications in referred journals on topics like Korn eigenvalues of quaternion matrices, linear preservers of semi-positive matrices, dynamics of non-negative matrix product, EP matrices, and generalized inverses, he has contributed significantly to the field. Let's welcome Dr. Sachindranath Jayaraman. Over to you.
Okay, so let me first thank the organizers for everything, the accommodation, the organization, everything. Yeah, so I'll be talking about quaternion matrix polynomials and location of their eigenvalues. And this is a joint work with Srinath and Pallavi. Very happy to see them here. Okay, so this presentation is organized into 3 sections. So basic introduction, and then I'll talk about quaternion matrices, and then quaternion matrix polynomials. Okay, so I'll denote by H the skew field of real quaternions, which consists of elements of the form A0 plus A1I plus A2J plus A3K, where the AIs come from the field of real numbers. And with the property that I squared equals J squared equals K squared equals IJK equals -1. And the conjugate and modulus of the quaternion are defined this way, which is quite standard. And I say that 2 quaternions are similar if there is a non-zero quaternion S such that S inverse QS equals P for some non-zero S. And this gives you an equivalence relation on H. And we'll denote by M and H the set of all n by n matrices over H. And given any quaternion matrix, we'll denote by A star the conjugate transpose, the usual definition. And other than this, positive semi-definiteness, positive definiteness can be defined in the usual way. And I'll denote by C plus the set of all complex numbers with non-negative imaginary parts. And yeah, that's what I will have for the introduction. So the next one is I'll talk about eigenvalues of quaternion matrices. So a quaternion lambda naught is called a right eigenvalue of a matrix A if there exists a non-zero vector X in Hn such that Ax equals X lambda naught, the usual way. And if you have a right eigenvalue, then any quaternion that is similar to lambda naught is again a right eigenvalue. So you can have infinitely many right eigenvalues. However, it turns out that given a quaternion matrix, there are exactly n right eigenvalues which are complex numbers with non-negative imaginary parts, and these are called the standard eigenvalues of E. So in most of these presentations, when I say location of eigenvalues, I will only work with standard eigenvalues, and therefore many of these will also work with right eigenvalues also. So, which means any right eigenvalue is going to be in one of the equivalence classes of these standard eigenvalues. But on the contrary, a quaternion that is...
What is standard eigenvalue? What is standard eigenvalue?
A standard eigenvalue is a complex number. It is an eigenvalue. It's a complex number with non-negative imaginary parts.
Non-negative imaginary.
It's in the I've defined it. But on the contrary, a quaternion that is similar to a left eigenvalue can be defined very similar to a right eigenvalue. So a quaternion that is similar to a left eigenvalue, it need not be a left eigenvalue. So it remains unknown if an n by n matrix, whether it has finitely many left eigenvalues. I mean, there are questions which are not very clear about left eigenvalues.
Two quaternions.
Yeah, two quaternions.
Similar, what do you mean with similar?
Yeah.
Okay, alpha and beta, two quaternions.
Yeah.
They are similar if and only what?
If and only if there is a non-singular, there is a non-zero S such that SP, S inverse is Q.
These are not matrices, they're just scalars.
Yeah. So let me proceed. Any quaternion can be uniquely expressed as A1 plus A2J, where A1 and A2 are complex numbers. It's very easy to write this way. And therefore, if you take a quaternion matrix, you can easily write it as A1 plus A2J, where A1 and A2 are complex matrices. And therefore, given a quaternion matrix, you can decompose this by you can form another matrix, a 2n by 2n matrix, defined as A1 A2 minus A2 bar A1 bar. And this matrix is called the complex adjoint matrix of A. Some people also work with the transpose of this matrix, this block matrix. So in some sense, so basically what you are doing is you are putting a copy of M and H into M2NC.
What is
using this?
What is bar?
Yeah, bar is just the usual conjugate. The usual conjugate. Elements with the conjugate. So basically, you are putting a copy of M and H into M2NC. That's what is happening. And in some sense, one can also think of this as you're having a C conjugate linear algebra automorphism of M2NC, where the subalgebra fixed by this map is going to be the set of all quaternion matrices. So anyway, I'm not going to use any of this, but and yeah, and of course you can define the Frobenius norm and the 2 norm in the usual way, just as you define for complex matrices. Okay, and I'll be making use of some of these properties, not everything, but some of these for when I do something later on, when I prove some results later on. So in particular, I'll be using this third result that A is non-singular, diagonalizable, normal, unitary, positive definite, if and only if the complex adjoint matrix is non-singular, diagonalizable, normal, unitary, etc. And other than this, the fifth and sixth statements that if lambda1 to lambda n are standard eigenvalues, if and only if lambda1, lambda2, etc., lambda n, lambda1 bar, lambda2 bar, etc., are eigenvalues of the complex adjoint matrix. And other than that, the standard, these routine identities involving the Frobenius norm and the 2 norm. Okay. We now move on to quaternion matrix polynomials. So an n by n right quaternion matrix polynomial of degree m is a function p from h to m and h, which goes as follows. P of lambda is summation I equals 1 to m ai lambda power I, where ai's come from the set of n by n matrices over h. And they're non-zero. AM is non-zero, usually. Of course, you can also talk about a left quaternion matrix polynomial, where the coefficients, matrix coefficients come on the right side. Yeah, and very similar to the matrix case, one can talk about left and right eigenvalue for a quaternion matrix polynomial. So a right eigenvalue for a right quaternion matrix polynomial is one for which summation I equals 1 to m ai x lambda naught power I is 0 for some non-zero vector x, the usual way. And we say that a scalar is a left eigenvalue if a similar one happens, if a similar identity is. So it turns out that if you have a right quaternion matrix polynomial of size n and degree m, then you can associate another polynomial to P by looking at this monic polynomial. And it turns out that the companion matrix, the block companion matrix, the eigenvalues, the right eigenvalues and left eigenvalues of the polynomial P are precisely the same as the eigenvalues of this block matrix C. And therefore, we define the standard eigenvalues of the matrix polynomial, a right matrix polynomial, as the eigenvalues of this matrix C. Okay, so with this, I'll point out something that happens with quaternions, but a difficulty with quaternions. You see, the eigenvalues of a complex matrix polynomial are exactly the same as the roots of its determinant, which is a scalar polynomial. But unfortunately, for quaternions, the quaternion case, this is a difficult one, because you look at this polynomial P, which is identity times lambda plus the diagonal matrix minus k and 1. It turns out that minus k is always an eigenvalue of P with eigenvector I plus j and 0. But minus k is not a root of this determinant lambda minus k. Therefore, you can't work with the classical determinant function. So there is a difficulty in working with this. So to work with this, now we see how to overcome this. So what happens is, let me, this is the whole purpose of my talk. So I will define what is known as stability and hyperstability of matrix polynomials. I will start with this the complex case. So if you have a matrix polynomial with complex coefficients, a complex matrix polynomial, and a non-empty subset omega of C, then you say that P is stable with respect to omega if for each non-zero vector y in Cn and each scalar mu in omega, there is a non-zero vector z such that z star p of y, p of mu times y is non-zero. Now it turns out that P has no eigenvalue in omega, but only if this polynomial is stable with respect to omega. There is also a much stronger notion of stability called hyperstability, which goes as follows. P is hyperstable with respect to omega if for each non-zero vector y, there is a non-zero vector z such that z star p of mu y is non-zero for all y in omega. And it's obvious that a polynomial is hyperstable, then it is always stable. But they're not equal in general. Okay, so what happens in the case of quaternion matrix polynomials? So the definition is very much the same, except you can't write this polynomial, you can't write this expression as z star p of mu y because of non-commutativity. So you have to expand this expression the usual way. And then you have a usual definition of stability and hyperstability. And it turns out that there are some nice results So the first one, so the natural question that arises is what happens with a scalar polynomial? So it turns out that for a scalar polynomial, for any subset omega of h, the polynomial is stable with respect to omega if and only if it is also hyperstable with respect to omega. And very similar to the complex case, one can prove that if you have a polynomial, a matrix polynomial, and you have a non-empty set omega, then P lambda has no eigenvalue in omega if and only if it is stable with respect to omega. And of course, you can, very similar to the complex case, you can talk about the numerical range of a polynomial. It is defined as all scalars in H such that y star am y lambda m plus dot 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 plus up to y star a naught y is 0 for some y in Hm. So this is just so if you look at the polynomial, the monic polynomial, linear matrix polynomial lambda I minus a, then this definition reduces to the classical numerical range, the usual definition of the matrix case. But unfortunately, even for lambda I minus a, although the numerical range is a closed set, this can never be, it need not be a convex set. You can have more than one connected component for lambda I minus a, even in the complex case. So it's a much more complex object than the matrix case. The matrix case where it is a convex compact set by the Hausdorff-Toeplitz theorem. And it turns out that if you have a polynomial, a matrix polynomial, and a subset omega contained in H, then the following conditions are true. Omega intersection with the numerical range is empty. P lambda is hyperstable with respect to omega. It is stable with respect to omega. So if you look at these three statements, it turns out that A implies B and B implies C. But the reverse implications are not always true. So I'll give an example. But one can also prove that similar to the way one defines the complex adjoint matrix of a matrix, one can also define the complex adjoint matrix polynomial, which is going to be a complex matrix polynomial for a polynomial. And it turns out that if you have a polynomial P, the matrix polynomial, then P is stable or hyperstable with respect to omega intersection C, if and only if it is the complex adjoint matrix polynomial is stable or hyperstable with respect to omega intersection C. So you are basically coming down to omega intersection C. So here are some examples. So the first one, you look at the polynomial, the linear matrix polynomial, lambda I minus a, where a is just the matrix 1, 0, 0, 0. It's easy to compute that the numerical range is the interval 0, 1 in R. Moreover, the only eigenvalue of P are 0 and 1, and therefore the polynomial is always stable with respect to H, take away 0, 1. It turns out that this polynomial is also hyperstable with respect to omega. But the intersection of omega with the numerical range is certainly non-empty, which means two of the conditions B and C in the previous theorem doesn't necessarily imply that the first condition is true. Now the second example, if you look at this quadratic polynomial, 1 lambda, lambda, lambda squared plus 1, then it turns out that this polynomial is stable with respect to any subset, now any non-empty subset of H, and therefore in particular with respect to the unit ball, but it is not hyperstable with respect to the unit ball. It can be proved. Okay. So how do you verify stability or hyperstability of a given matrix polynomial? So we begin with some notation. So let's look at the standard one, the closed unit ball and the open unit ball in H. And some easy consequences about two complex numbers with non-negative parts, non-negative imaginary parts. It turns out that if you have a polynomial, let's say monic polynomial, and you look at the unit ball centered at a complex number of radius r, then P is stable with respect to the intersection of this ball with C, if and only if it is stable with respect to the ball centered at A bar with radius r intersection with C. So there is something, you're coming down to the complex number, you're coming down with some other, you're trying to verify stability with respect to a different set. So what happens is that if you have a set omega, which is an open ball in H centered at A of radius r positive, then P is stable with respect to omega if and only if P is stable with respect to omega intersection C. So you are coming down to the complex plane to verifying stability. It's a much smaller set now. But it turns out that this theorem is no longer true if the center of the ball is a pure quaternion and not a complex number. And there is an example as well. And it also tells you that you can't prove this theorem for any convex set. You can only do this for an open ball whose center is a complex number. Okay. We now move on to sets that are stable for quaternion matrix polynomials. So what I do is you take a quaternion matrix polynomial where the coefficients am and a0 are invertible, and I associate two scalar polynomials involving their two norms as follows. Then it turns out that P is stable with respect to the open unit ball where r, the radius of the ball, is a zero of this polynomial L. And similarly, you can prove that the polynomial is stable with respect to H complement the closure of this ball centered at capital R, where R is the unique root, positive root of the polynomial U of Z. So you combine these and you can derive that the right eigenvalues of a quaternion matrix polynomial with invertible leading and constant coefficients, it will always lie in the annular region small r to capital R. But I wish to point out that there are some remarks here. So these bounds, these bounds R and the small r and capital R are always achieved. It also turns out that if you have a unitary polynomial, a polynomial with unitary coefficients, then one can prove that the right eigenvalues are always inside this annular region 1/2 to 2. Of course, we didn't derive this. We can derive this second statement using different methods, not involving any of this. Okay. So what do I get out of all of this? There is a classical theorem in complex analysis which goes as follows. If you have a scalar polynomial, a complex polynomial with real coefficients satisfying this monotone condition with am bigger than or equal to am minus 1, bigger than or equal to am minus 2, dot, 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 bigger than a naught, with am bigger than 0, then any 0 of the polynomial satisfies this condition. Actually, the classical version only says that these zeros lie in the closed unit ball, but one can also deduce this version too. This is called the Iwsmga theorem. It's a typical 4 minutes. Okay. And turns out that you can also prove a version of the Iwsmga theorem for a quaternion matrix polynomial whose coefficients are positive definite, say obeying this order condition. In which case the right eigenvalues are always in this annular region. This mod lambda naught is less than or equal to 1, and it is always bigger than or equal to the largest eigenvalue of A naught divided by 2 times the the smallest eigenvalue of A naught in the numerator divided by 2 times the largest eigenvalue of A naught. I'll skip the proof. I'll end with this one. So the natural question is, when will stability imply hyperstability? Now, as pointed out earlier, if you look at this polynomial, this quadratic polynomial I2 lambda plus diagonal minus k comma 1, then minus k is an eigenvalue, but it is not a root of lambda minus k. So what we do is to overcome this, we define what is called the p determinant of a matrix polynomial. And it turns out that this p determinant, with this p determinant, one can prove that if you look at the linear matrix polynomial, then lambda naught is an eigenvalue of p lambda if and only if it is a 0 of the p determinant. So here is the final one. It turns out that the p determinant can also be related to a complex, polynomial, a quaternion polynomial as follows. So if you have a polynomial with a monic polynomial with quaternion coefficients, then lambda naught is an eigenvalue of p if and only if it is a 0 of this scalar polynomial. And I'll end with this final theorem. So if you have a polynomial, a matrix polynomial with leading coefficient to be the identity matrix, and if omega is any non-empty subset of H, then P is hyperstable with respect to omega if and only if it is stable with respect to omega when P is an upper triangular matrix. It's an upper triangular matrix polynomial. So I'll end with this. So most of these theorems, many of them are proved in the complex case, assuming that P has this form, that P of lambda times A plus Q of lambda times B. For some scalar polynomials P and Q, and A and B are complex matrices. And the proof uses something called as the generalized Schur form. But unfortunately, you can't do this in the quaternion setting unless these matrices are complex matrices and the variable itself is a real variable. So this is something that you have to avoid in the case of quaternion matrix polynomials. And I'll end with one final one. So far, we have only talked about right eigenvalues and standard eigenvalues. But what about left eigenvalues? So one can also define a notion of stability very similar to the usual one, which is called the left stable with respect to a non-empty subset omega. And it turns out that a polynomial is left stable with respect to omega if and only if it has no left eigenvalues in omega. And many of the results will carry over, but not all, because a quaternion that is similar to a right eigenvalue is again a right eigenvalue, which is no longer true in the case of left eigenvalues. So it's not very clear if everything goes through with this notion of left stability. And it's not also clear whether the P determinant will carry over with respect to left eigenvalues. That's all I have.
Thank you.
And most of this, everything is from the first one, the first paper, and here are some references.
Well, any questions? Any questions? Yes.
Thank you, sir, for the nice talk. Just I was wondering what happens to octonions wherein they are not associative. How much of associative property have you used in your proofs?
Associative, I mean, for octonions.
Yeah, they are not associative. So
I have not tried.
okay. So it's basically if you have complex numbers, you arrange those 4 complex numbers in the matrix. Very similarly, if you arrange the quaternions in the matrix, you'll get octonions, and they are not even associative.
I'm not tried. I think about it.
Yeah.
Any other question? I was wondering that Jacobson does work. Jacobson book has a lot of work on the matrices over the non-commutative fields. Quaternions are fields, but not commutative. And he does talk about right and left eigenvalues. Have you seen what is, so why can't you do it something over the non-commutative fields rather than just special case, which is quaternions? Is that, what's the motivation of using quaternions?
I don't know. I have to think about.
Yeah, look at this Jacobson work. Yeah, okay. Anybody else? Anybody else, please? If not, we thank the speaker again and go for lunch.
We have one more talk.
One more time?
We have one more.
Excuse me, I thought I was finished. I was asking for lunch. Okay. Okay, I'm so sorry.
We can start.
Okay, we can start. The next speaker is, I'm so sorry. The next speaker is K. Dukadi, P. Srinivas from local Manipal.
Let me introduce the speaker. Dr. Kedukodi Babushri Srinivas is a professor in Department of Mathematics at MIT Mahe, Manipal. His research focuses on algebra, nearing theory, rings, n-groups, graph aspects, algebraic hyperstructures, algorithms, rough set theory, and fuzzy set theory. He co-authored books Near Rings, Near Fields, and Related Topics in World Scientific in 2017, and has published several papers and conducted collaborative research visit to Az University in Iran and Ohio University in USA. Let's welcome Dr. K.V. Srinivas, sir. Over to you.
afternoon. Yeah, good afternoon to all. I first of all thank Professor Manjunath Prasad for giving me an opportunity to give this talk. I'm sorry, I'm between you and the lunch, so okay. Please bear with me. Yeah, so this is joint work with Dr. Aishwarya IAS and Professor Kunchum Sham Prasad. It's about formal commutative proofs and abstract syntax trees. I'll just tell how we got into this. We were studying basic distributive laws, wherein A plus B into C is AB in AC into plus BC, school level distributive laws. C into A plus B, you distribute CA plus CB, basic distributive laws. And we wanted the proofs to be verifiable by machine. So whatever proofs we write should be verified by a machine. So the thing is, in that case, we want it to be language independent, and we also want it to be machine independent. Okay, so these two criteria are required, and we don't want to lose the geometry behind the proofs, or we want to see the proofs in some sense. And the simplest thing we could think about was, of course, graphs. And inside graph, the simplest thing was trees. So that's how we got into trees. So that justifies the abstract syntax trees. That's how that part comes. And the first part is formal commutative proofs. And what is happening here is the world is going towards that, wherein people want the proofs to be verified by machines. Okay, so that's the idea. And as soon as we got into trees, we realized that, okay, even things have been not done, forget rings, it's not being done in just groups. So we had to start from that. And please bear with me for the definitions which will follow. Of course, we'll directly get into example of a tree. So let us take this expression of the form x star y plus z. So something like this, we can represent it by a tree, and we can go from left to right. So x star y plus z. So that's how that tree can be read. But we can also read it, this is left to right, we can read it in the other way around. Okay, z plus y, then star x. Okay, so that's the way we can read it. It's one tree, but you can read it in two ways. So here itself, things start becoming interesting. Of course, LR is different from R. Okay, so, and of course, we have to start with equality. For example, A plus B equal to C plus D. We can read it from left to right. A plus B is equal to C plus D in the LR traversal. So we have to start right from the basics. Of course, associativity. And you can see in the LR order, the associativity goes like this: A plus B plus C, and A plus B plus C. So that is the LR traversal. Of course, it doesn't matter here when it comes to associativity, both mean the same. Okay, if you traverse it from the right, it looks like this: C plus then B plus A is same as C plus D plus E. So both are equivalent when it comes to associativity. So there is no difference. So just one of the conditions is enough, either LR or RL. So existence of identity, again, here we see in some way in terms of picture what is right identity and what is left identity. You can see if you read it in LR order, A plus E equal to A. So what we get is nothing but the right identity. But if you read it in the other way around, RL order, so it is E plus A equal to A. So what we get is left identity. So it is able to distinguish between left and right. Of course, moment left identity, right identity is there. Of course, we have to start from groups itself. Of course, it gives rise to inverses, left inverse and right inverse. So in general, this need not be same. So this is existence of inverses, and this is commutativity property. A plus B is same as B plus A. Usually, of course, let us go into some geometry or linear algebra, how A plus B is B plus A in terms of vectors. What we can do is imagine parallelogram law, how we add two vectors. So 0 is there, A is there, on the other side B is there. So what we do is from A, we draw something parallel to B, and from B, we draw something parallel to A. So A plus B is same as B plus A. That's why you say diagram commutes, and that's why you say A plus B is same as B plus A, it is commutative. But the same thing we can see in terms of this abstract tree. It is, if you traverse from left to right, it is A plus B, right to left, it is B plus A. So it's a discrete way of looking at things. So although the diagrams are simple, there is something very nice going on here. So A plus B diagram commutes in some sense. LR and RL, if they are same, we get this. Of course, what happens is something like if you take a Rubik's cube, etc., it is not, the group is not abelian. So if you turn one rotation after the other, it is not the same as the other way around. Okay, so A plus B need not be same as B plus A in general for a group. Okay. So this is about groups. Of course, immediate things that come into picture in groups is cancellation. This we will be using heavily. So this is the right cancellation. If this part is same, the right part plus C is same, we can cancel it out. Very similarly, we can define left cancellation. Okay, so let us take a group and let us define addition as pointwise addition. F plus G is f of x plus g of x. Composition of mappings, we can define these two things given a group. Group is with binary operation plus in it. Okay, so what happens is in the group, what you can see is, let us look at this F plus G composition H. It is F composition H plus G composition H. Okay, so let us go from left to right. So you can see F plus G composition H. That's what is this part is F composition H and G composition H. So this is always true. Okay, but this is LR order. We are going from left to right. But let us do it in the other way around. H composed with G plus H. So this is in general not same as the right hand side. If at all this H, G, F, they are linear or endomorphisms, then you can distribute. So very nicely we can see in terms of some pictures, this is true. Left to, of course, LR traversal, it is true, the right distributive law holds, but RL traversal, it is not true. Okay, so this gives rise to a structure called as near ring, okay, wherein only one of the distributive laws need to hold. Okay, if both distributive laws are true, then what we get is a ring. So we have a nice way of introducing the topic itself near. Okay, so this is the associativity. We can define nearing in terms of syntax trees. This is associativity. Any one of the associative, what I mean to say is one of the traversals is good enough because both are equivalent. But when it comes to distributivity, those are not equivalent. Okay, so this is, of course, the distributive laws, and this right to left traversal, it need not hold true in general. Okay, so this is the definition of a nearing in terms of abstract syntax trees. Okay, so definition of ring is both the traversals should hold. Okay, so that's the definition of the ring. So both the distributive laws should be true. So let us do something very simple to see whether things are working fine or not. Something like 0 into A is 0. Of course, this is true in near ring, and in the ring A into 0 is also 0. But in near ring, only one-sided multiplication activity by 0 absorption happens. Okay, so that's is the case. 0 into A is 0, but A into 0 need not be 0. So let us do a very simple proof using trees. So what we do is we take 0 star A, so we can write it this 0, we can replace it by 0 plus 0, and of course 0 is the identity. So use right distribution, we can write it in this format. And what we note is, of course, this happens, and the simplification gives these two parts are exactly the same. So what we can do is we can cancel it out, use the right cancellation law, which we spoke about, and what we get is 0 star A is 0. But if we try to write the same proof in, this is in L to R order, try to write the same proof in R to L fashion, you won't get it because we don't have the cancellation law and we don't have the left distributive. So a simple example you can take is take f composition 0 of x, we will get f of 0, and f of 0 need not be 0 in general. But in the other way around, 0 composition f will come as 0. Okay, so the just if you try to go through the proof in RL order, it won't be true, but LR order, it is true. Okay, so see some simple proof to begin with. Okay, so this is concept of primeness. Of course, Professor S.K. Jain talked about zero divisors. In some sense, these are highly related to this. So this is A and B equal to 0 is A equal to 0 or B equal to 0. So definition of 3 prime ideal. There are different kind of prime ideals in near ring. So one of the famous one is called as 3 prime ideal. And Professor Andre Leroy, he gave a talk day before yesterday on what is called as gamma derivation. Okay, so you can see the definition of derivation over here. So what we can do is, this is called as a sigma derivation. And if you take that sigma, this part as 0, and tau equal to identity, so then what we get is basically that sigma derivation, which was introduced by Professor Andre, and you have seen on the talk. And in this case, to keep everything simple, we will take tau and sigma as identity maps just to go through the ideas. But if you take tau and sigma as any other maps, still the idea of the proofs hold. Okay, so question is why these gamma derivations? Okay, so let us see something very simple. You might have heard about Pascal's triangle, which basically says NCR is NC n minus R. It leads to something like commutativity of complex numbers. Okay, so the symmetry of Pascal's triangle, it induces commutativity of complex numbers. So this is like something similar to butterfly effect. Okay, some small thing happening somewhere, it leads to some very big unexpected thing. And if you try to prove, it's not that trivial to prove. Just commutativity coming from symmetry of Pascal's triangle. So this is surprising, and this we had, of course, a more general result was proved, wherein we had to just choose some ideals, that's all. So if you take a ring as C and the semigroup ideal as C itself, the choice of gamma has to be done nicely. That's where Pascal's triangle comes into picture. And you can see, of course, Pascal's triangle, it is very famous. In fact, the first algorithm was written to find these numbers in the Pascal's triangle. So it is fundamental in various ways. Of course, when I say symmetry, it is symmetry about this vertical line. NCR is NCN minus R. That gamma needs to be, this function gamma needs to be symmetric, and that comes because of the symmetry of NCK. Okay, so because of the symmetry of this Pascal's triangle, I get symmetry of this gamma, and because of this symmetry of gamma, we get symmetry of in the gamma derivation itself, and that we use nicely to get commutativity of C. So gamma derivations are very interesting, very nice ones. Okay. So we take gamma derivation, and our aim is to get some commutativity results. If there is a prime ideal and derivation in a ring or a near ring, it turns out to be commutative. So those commutativity results we are trying to prove. And we require some help of some extra definitions. For example, what is gamma left immersive, right immersive, etc. In this case, that C goes B into C is treated as B only. So it is going off. So we call it as right immersive. So this property comes. Of course, if you take a constant function, it is true, it satisfies that case. If you take any constant function, that's a simple example wherein it satisfies this. Of course, this is the definition of course, this is the proposition, and this is how we get hold of that left distributivity. So you can see this A distributes over all. Okay, so if we have a derivation, and we can call this as partial left distributive law, because all inside things they are at least made up of product of two values. So we can distribute this, of course, moment we have a gamma derivation. That's the proof which we'll try to do it using abstract syntax trees. So this is the proof, at least one proof we'll try to understand. Okay, so we begin with the proof. This is true, this is the associative law, and we apply D on this. So D of this should be same as D of this, and we will try to simplify the trees. So that's what we will do. So we will start with the first one, D of this. So we will use the definition of D. Of course, this is the definition. So this is expanded, and definition of D is being used. So it is getting expanded, and we will use right distributivity. So that's what, of course, it's a new thing. So we have to be little comfortable looking at those big pictures. But once we get used to the new language, that is easy. But very carefully, we have to look at those exams and apply and simplify. So this is being done here. And here comes the part of left immersive. So we will use that it is left immersive, so that A vanishes. So this A into B becomes same as B. So it is left immersive. So that part is being used. And very similarly, now we will use the secondary, do the similar simplification. And now I require the definition of right immersivity. So the right part goes away, only that A should remain. And if you equate those two trees, what we get is the situation like this. And we can see that this part is same as the last part. So we can cancel it out using the right cancellation laws. And now we will concentrate on this part, keeping the right hand side same. In this part, we will use the associativity. of course, this part we will use the associativity. So we will get something like this. Now we will use the associativity of plus in these three. And what we find is, again, this part is same as the last part. We can cancel it out. And once we do that, we will use the associativity of star and we will get these two trees. And now this is what we were trying to do. So let us look at the right hand side. So it is A star. Then we will calculate this left to right we will go. So B D of C, B star D of C. And if you can go on simplifying the tree from left to right. Okay, very similarly, you can go on simplifying the tree from left to right. For example, A star we will get, B star D of C we will get, simplify the left hand side. So what happens is, if we do this, you can see that this A distributes overall. Okay, so this is step by step things worked out on ASTs. Okay, so this is how it is verified and written in terms of tree. And we'll go to commutative proofs. Of course, I require two results from paper of Bell. If you have a 3' nearing, and if you take X not in the center, then X can't be a zero divisor. And a second proposition I require. So it says if K is a subset of Zn, then the whole nearing becomes commutative. Of course,
Again, one more time, what?
Zn is multiplicative center. And that K is a semigroup left ideal or a right ideal. And of course, this is a typical commutativity result, which is going to be proved using abstract syntax trees. Of course, we make use of gamma derivation, we make use of 3' nearing, we also make use of semigroup left and right ideal. And I'll just show the sketch of the proof. Of course, we bring down the graphs of the trees such that the cancellation laws are possible. And I'll just show the proof. It is very similar to the kind of calculations are similar to what we have seen. Basically, we have to simplify the trees such that the cancellation laws are possible. So you can see we start with some left hand side, we start with right hand side, and we will go on simplifying the left hand side, use those axioms, simplify the right hand side, and you can see a big cancellation possible. Of course, we do it very, very carefully in the sense we use each and every step. For example, it is visible, we don't cancel like that. We use the property one step after the other. Now associativity has to be used. Using associativity, we will cancel it out. So each step is getting verified. We don't take it for granted any axiom. So once we cancel, we get something like this. So this says that A commutes with every element of K. And now we build out, this is like step 1, and step 2 and step 3, we make use of left ideal, semigroup left ideal, semigroup right ideal, and we build the same proof. It involves some 12 steps. So we build out, this is the 6th step, maybe this is the 12th step wherein everything gets winded up, and there is a big cancellation which will happen. And what we get is something like this. And using those two propositions, we can prove that N is commutative.
Nice. Yes, please. Any questions? Any questions? Well, I have a question. It's just a curious question.
Yes, yes.
You're talking about commutativity, right? By Austin, there's a lot of this kind of work. Austin.
Yes, yes, sir.
one of the question was, if some power of AB is equal to some power of BA. Let's say in your case, AB whole square is BA whole square. And can you just make any sense in this case? Does it, if AB whole square is equal to BA some power?
I think if those cancellation laws are true, then it is fine. If there should not be any zero divisors, then it is true. But of course, I have not thought about that. Maybe I can think in terms of.
Does it make any sense? In the case of this kind of nearing.
Yeah, because in general, AB need not be same as BA.
Yes.
Let us take.
Yes, correct.
Yeah, but there are some
powers are equal.
Yeah, I think there are proofs wherein, of course, in terms of let us take group, just let us take group. In that case, AB power n is same as BA power n. It implies that the group is abelian. But yeah, but in case of ring, we don't have those cancellation laws. So it depends whether the ring has a zero divisor or not. So if you have such a thing like field type of restriction,
Yes.
then it will come.
No, you assume. See, this was proved by Nagore Mathematics General. By
Okay.
Herstein, me,
Okay.
and one more person.
Okay. I am
So
not.
we had proved this result for the general
Okay.
rings.
Okay.
Now I was asking a very similar thing.
Okay. Okay.
You take even a where you can have inverted. You
Okay,
can first you do for division.
Okay. Okay.
If some power of AB is some power of BA, does it imply commutativity in the
I have to think. Thank you. Thank you.
It is in the Nagore General Mathematics.
Oh, okay. I'll contact you soon. Thank you.
Well, any other question, please? If none, thank you, the speaker, and for the nice and interesting talk. And now I think we have time for lunch.
Thanks.
We thank Professor S.K. Jain sir for chairing this session. So the contributory talk is from 2:15 to 3:10 in NLA with academic block 3. And from 3:15 we have online talk by Professor Simo Puntanen in this venue itself from 3:15. So we'll now break for lunch. Thank you.
I'm cold here. Are you cold?
Yes, it's cool.
I'm cold.
You don't have a what full
Full,
sleeve.
full sleeve, yes.
Full
I
sleeve
thought
is
I.
better.
Yes.
If you don't want, you can just fold it, no?
That's right.
That's right.
I will like to be watching for that.
Might be very hard to get.
Academic side ಇದೊಂದು ನಿಮಿಷ ಸ್ವಲ್ಪ ಸೀರಿಯಸ್ ಆಗ್ಬೇಕು.
ಮಾತಾಡಿದ್ರು
ಅಂತ ಬಯಸಿದ್ರೆ ಅವರು ನೀವು ಸ್ಟಾರ್ಟ್ ಆಗಿರ್ಬೇಕಂತ ಮೂವ್ ಮಾಡಿದ್ರೆ
ಅಲ್ಲ ಅದು ಕ್ಯಾಂಡಿಡೇಟ್ ಬರ್ಬೇಕು.
ನೈಸ್
ಆಫ್ಟರ್ ಇನ್ ಲಂಚ್ ಬ್ರೇಕ್
ಕುಡಿಬಾರ್ದಂತ ಸುಮ್ಮನೆ ನಾವೇ ಕುಡಿಬೇಕಂತ
ನೀವು ಊಟಕ್ಕೆ ಬರ್ತೀರಲ್ಲ ಈಗ?
ಹೌದು, ಎಲ್ಲ ದೂರ ಎಲ್ಲಿ ನಿಂತು?
ರಾಣೆಬೆನ್ನೂರು ಹಾವೇರಿಗೆ ಹೇಗೆ ಹೋಗ್ತೀರಿ ಬಸ್ಸಿಗ?
ನೀವು ಕರ್ಕೊಂಡು ಹೋಗ್ತಿರಲ್ಲ? ಅಲ್ಲ, ಊರಿಗೆ.
ಊರಿಗೆ ಬಸ್.
ಇದು ಚೆಕ್ ಸರ್, ಸರ್ ಲೈವ್ ಆಗ್ತಾ ಇತ್ತು, ಫೋಟೋ ತೆಗ್ದು.
ಆಡಿಟೋರಿಯಂ ಚೂರು ಕಜ ಇತ್ತು ಕಣಿ. ಆಡಿಟೋರಿಯಂ ಅಲ್ಲಿ ಚೂರು ಕಜವಿತ್ತು ಕಣಿ. ಹತ್ತು ಬಾಬಾ ಇತ್ತೆ. ಹಾ ಅದ 10 ಪೋಲೆ ಬಾಬಾ. 10 ಪೋಲೆ ರಪ್ಪ. ಉಂಡು ಬಾಬಾ ಅಲ್ಲಿ ಮತ್ತೊಂದು ಬಲೆ. ಇಜ್ಜಿ ಬಾಬಾ ಪ್ರಾಮಿಸ್. ಬಾಬಾ ಬಕ್ಕ ಇಕ್ಕಟ್ಟಿ ಅರ್ಜೆಂಟ್ ಹಾಕುದು ರಪ್ಪ ಬಲಿ. ಓಪನ್ ಮೇಲೆ. ಹಲೋ. ಬೇಗ ಬರ್ತೇವೆ. ಓಪನ್ ಬಂದೆ. ಬಂತು?
ಈರಲ್ಲಿ ಪಟ್ಟಣ
Kalau mau baik ke dalam sih, kalau
ಅದೇ
manjawa.
ಹ್ಮ್
ಬಜ್ಜಿ ಏನೇ
ಗೊತ್ತಿತ್ತು.
ಒಂದು ಕೊಡ್ಚೆ ಒಂದು ಕೂಡ ಪ್ಲಾಸ್ಟಿಕ್ ಒಂದುಂಟಾ
ಯಾವುದು? ನಾವು ಜಸ್ಟ್ ಮುಲ್ತ ಅಲ್ಲದೆ ಉನ್ನ ಒಂದು ನಾತೆ
ఇక్కడ
ರೆಕಾರ್ಡ್
నేను పాడేది నేను పాడేది
ಆಯ್ಕೆ ಮಾಡಿದ್ದೀನಿ ಬರ್ಲಿ. ಆಯ್ಕೆ ಮಾಡಿ
ಮುಂದೆ
ಆಯ್ಕೆ ಮಾಡಿ ಬರ್ಲಿ. Actually, for avdi vada andre. Actually, for avdi vada. Actually, for avdi vada.
ನೆಕ್ಸ್ಟ್ ಡೇ ಹೋಗಿ ಬರಬೇಕು ಅನ್ಕೋತೆ
ಅವನ್ ಪ್ರಶ್ನೆ ಒಂದು ಹೋಗ್ತಿದೆ. ಏನ
I called, he told he will come. Okay, okay, sir. Here, the plan. Okay.
So this is one from Yeah.
Hello, Professor Puntrul.
Hello, hello. Hello, India. Greetings from Nokia.
Hi.
Do I have
No, it's on to increase.
9 minutes to go?
Oh, it's not. Sometimes, yeah, we can see, sir. We can see you, sir.
Very good. You can see me.
Okay, I got it.
Very good. Do I look good?
Okay, shall I press something? No, it is too much voice sound, I think.
All right.
Yeah, maybe half. Half is correct. Sir, can you hear us?
Yes, I can hear.
Yes. Yes, sir. Participants are yet to come. They are in the contributory talk in some other building. We may start at 3:30.
Yes, in 8 minutes, around
Yeah,
8
some
minutes.
8 minutes.
Okay.
Okay. Here. Hi, Simo. Video ಇಲ್ಲಿ ಬರ್ತಿಲ್ವಾ? No, video is coming here. He has to talk there? Steve. Yeah? Oh, I have to talk over here. Fine. Yeah. Yes, there is a mic right. Oh, okay.
You know, this camera is off, I think.
Hi, Simo, are you there?
Hi there, Steve.
How are you doing?
Oh, he did not. Is it off?
No, I think he didn't speak. Can you ask him to talk?
Simo, can you test the mic, please?
Yes.
Yeah.
Okay, you're there. Excellent. So,
Camera.
there he is. Okay.
What are you trying to go?
Pardon, say it again.
No, I'm just wondering what you are trying. Are you trying to share some slide or what?
Yes, definitely. Are you ready for my slides?
I'm not yet ready. We have more than 5 minutes time.
Yes, okay. Should I put them on?
It is nice that you have joined online. Okay. And probably you will be delivering technical talk for some time.
Sorry, I could not catch.
You are delivering a technical talk for some time.
Yes.
Am I right?
Yes.
Then later, towards the end of the talk, you can continue as a member of scientific committee and speak for some more time.
Yes.
Okay. Then later we will continue with the valedictory session.
Yes.
Is it fine?
Yes. Half an hour will do. Half an hour will do for the whole show.
Whatever. Okay. Please. Okay. Then later you can continue with the whatever you want to speak as a scientific committee member. Okay.
Yes.
You got it? Okay. What is the time now? 8:25. In fact, yeah, I'll request Steve to chair this session. Simo? Disconnect. He must be taking his son's help.
Okay.
Okay. I'm requesting Steve to chair this session. Steve is here with us. Steve Kirkland. Are you with me?
I am, but Steve.
Yeah, please, Steve, come forward.
Okay.
Yeah, we'll start. Yeah, where are those people? They are still. Okay. Shouldn't still going on. Okay. Okay, we will proceed as per time so that those people will come and join with us. Okay, then we'll proceed.
Okay.
Yeah. Yeah. Please.
Okay.
Okay, whatever.
Okay, good afternoon, everyone. Welcome to the final, and for Simo's benefit, I'll say the ultimate talk of this conference. So I'm happy to introduce Simo Puntanen from University of Tampere in Finland. Simo's a longtime friend and organizer of the series of ICLAA meetings. I was hoping that he'd be here in person, but the visa deities said otherwise. But he's here on Zoom and going to talk to us about, I think you're talking about a paper of CRL, is that correct?
Yeah, that's correct.
Very good. Take it away, Simo.
Okay.
1 minute, sir. I will introduce the speaker now. So, good afternoon, everyone. It's my honor to introduce our distinguished speaker, Dr. Simo Puntanen. Dr. Simo Puntanen is a visiting professor at Tampere University, Finland. His research focuses on matrix methods in statistics, generalized inverses, and canonical correlations. A senior researcher of Academy of Finland from 1992 to 1995, he has published over 130 papers, co-authored 2 books, co-edited 8 books, and 16 journal special issues, and serves on 4 journal editorial boards, as per my knowledge now. He has served scientific and organizing committees for 65 conferences and workshops. Jointly with George P.H. Stein, he is a founding member of the International Workshop on Matrices and Statistics series. Please join me in welcoming Dr. Simo Puntanen. Over to you, sir.
Okay.
I think we are missing rights to share on Zoom.
And we can wait.
You would get
Yes.
I think now you can share, sir. You
Yes.
can try now. Yeah, we can see the slides.
Hello, are you all prepared to listen to my talk?
Yes, yes, sir.
Very good, very good. Take it a relaxed position and be ready. Yes, I'm looking out of my window and it is precisely midday. It is 12 o'clock here in Finland and we have no 1 bit of snow. That much about weather. But now I will talk about my talk and I will talk about some results in C.R. Rao's paper in Sankhya in 1971. How can I get the next slide? Okay. Now, yes, let's go 50 4 years back. And this is it. This is the paper that I'm talking about. 71 in Sankhya, Unified Theory of Linear Estimation. Here is the abstract, and this blue text is the first paragraph of this abstract. We consider the general Gauss-Markov model where expectation of y is x beta and covariance matrix of y is V. There may be deficiency in rank of X and V can be singular. This is the last paragraph of the abstract. Complete robustness of blues under different alternatives of V has been examined. Here are 4 question marks. And here are my 3 co-authors, Steve, Jarkko, and Augustin. And I'm happy to have recognized that Steve is not yet in bed. He is maybe watching this show from bed using his laptop. We consider 2 linear models for a given matrix V naught. MV naught as one model. Covariance matrix, there is a given matrix, then there is MV model, and the covariance matrix is V. That's something different. And following Rao in 71, we can search for the set of script V, which is a set of non-negative definite matrices such that every representation of the blue of mu under MV naught remains blue under MV. I shortly say often under V, which I mean under MV. Focus in this talk is that for a given V naught, how to characterize the set of script V, which is non-negative definite matrices, V such that every representation of the blue of mu equal x beta under MV naught remains blue under MV. I go very quickly through, actually I simply show these theorems of Rao. I will go into more details shortly. Here is the condition 5.1, which is the condition for the property that every representation of blue under V naught remains blue under V. Here Rao's M refers to column space. I'm using script C. Z is a matrix X perp, any matrix spanning the orthocomplement of Cx. The second theorem is 5.3, and the major difference lies here in 5.2 for formulation. This is explicit expression for the permissible covariance matrices that give the same blue as under V naught. And a third statement that Rao had. The difference here is that Rao has here V naught. It's added here. But he does not say, he only in 5.2 he says that A and B are symmetric matrices. Here he does not repeat that statement. And as we all know, Professor Rao passed away 2 years, 4 months ago. On September 23, he would have reached the age of 103. And let's go back to blue very quickly. If gy is a linear unbiased estimator for x beta under MV, then gy is the blue if the covariance matrix of gy is below the covariance matrix of Ly for any L satisfying this unbiasedness condition. So that's the definition of the blue. And if we denote by M the matrix I minus Px, which is one choice for the X perp, then Gy is blue if this equation star is satisfied. This is the crucial equation because it provides the presentations for the blue. It's this guy G here, what we are interested in. And some people call this as a fundamental blue equation. And that is very handy tool for checking, for example, whether a given estimator is a blue, etc. If k beta is estimable, then the corresponding fundamental equation is down here. So that looks extremely similar to what we previously had. Now, one well-known solution for G in this equation star is G naught, which can be written in this way. Display A here, where W is a matrix V plus XX prime. Now the general solution to this equation, let's say G sharp, can be expressed as this one solution plus n times I minus P W, and here n can be any matrix. It's free to vary. So that's a usual linear equation business. What this means that G sharp has this presentation, it means that because this n varies here, the solution here may not be unique. That's the reason why we are talking about various representations. The solution may be unique, but it is not necessarily. For the property that every representation of the blue or mu under V naught remains blue under V, we use short notation B mu under V naught is a subset of B mu under V. So we have these two models. V naught is a given fixed non-negative definite matrix. By Rao's first theorem 5.2 that I've earlier showed, he said that these statements are equivalent. CVM is a subspace of CV naught M. Then it means that every representation under V naught remains blue under V. Now we can keep everything else fixed in this equation. Star here, but we don't keep V fixed. And we are trying to figure out how to characterize the set of V's satisfying this equation star. And Rao had this formulation 1.2. V is of the form X, A prime X, etc. for some matrices A and B. So what's crucial here is that in between here and here we have non-negative definite matrices. Then without any problems, the resulting V is non-negative definite as well. And now it makes sense to rewrite the following three results of Rao more or less verbatim in his style. So this is the repeated slide about or formulation of Rao's first theorem. Consider the model MV naught, which is consistent in this sense 2.1. If the blue of every estimable parametric function under MV naught is also blue under MV, then when V preserves the consistency of V naught, then it is necessary and sufficient that this column space inclusion is holding. I will comment this formulation a bit later, but I can go to his second theorem. Rao assumed in his second theorem that the column space of X V naught is the whole space. The rank of the partition matrix is n. And then he said that it is necessary and sufficient that V has to be of this form where R and S are arbitrary symmetric matrices. Then every representation under V naught remains blue under V. And then he had the corollary, which was this more or less precisely as Rao wrote it. He said that it can be written as this 2.5. And that, to our team, we were really wondering, because he didn't have any proof for this. And we were really wondering how can it be done. I very well remember when Steve Haslett from New Zealand, who is now watching this, I hope, he said that, can I show him the proof of this? And I remember I was surprised because over the years I had been thinking that it is obvious, but it was not. Next, I will make some remarks on the above results, and it is worth saying that Rao did nothing wrong, but he apparently rather left something unsaid, and it was somehow very, very, we enjoyed going through these details or fine details of these results. I may mention that, by the way, the material of my talk has appeared in the latest issue of Sankhya, so our paper considerations were well treated. So here is one thing that I more or less said earlier. Rao wrote V in this form 2.6, but he said that R and S are symmetric, but they, of course, this resulting V must be non-negative definite. So we took that into account. And another thing that in his theorem 5.2, Rao assumed that the V preserves the consistency of V naught, by which he means the following, that if Y belongs here in this column space, then Y belongs also to this space. But this is not needed. Rao observed that himself later on. There's one common assumption which is very much needed in this consideration, namely if everything is correct in the linear model, then the observed value of Y has to belong into this column space, X and V naught. So X and V naught, they are definitely given, we know them. And then when we observe Y, if it is not in this space, then there's something very, very alarming. That statement may not be that interesting. And also this Rao requested that the column space of X V naught is the whole space Rn, but that is not needed. That is not needed in the proof. And the other thing, one more thing is that Rao said that in corollary that V has to be of this form where S and R are symmetric matrices. But this was our headache for some time until we could find a proof for that corollary. And here I have simply written the extended version of Rao's theorem in that way as we formulated it. So here V naught is a given matrix. We have two models. Then the following statements are equivalent. This first statement simply, it is a statement that every representation of blue under V naught remains blue under V. Then this is the Rao's condition, this B that I already showed. And here we have C, which is condition that V is equal to this representation that was already available. But in D, there we have additional thing. We have to assume that V is non-negative definite. And that is not fully trivial at all to take into account. And here, these are not, these are easy extensions. We have here a scalar sigma squared here, and that's very easy to observe that one can have that there. Actually, we can have a closer look at the following two statements. We have A prime here, B prime in here, and then we have set D. V is here, this guy that belongs to this group, it is non-negative definite, but here R and S are symmetric. And now it's easy to see that from C, if it take one matrix from here, we can express it in this form. That is obvious. But to go the other way, it's not trivial. It requires a trick. I will simply show the tricks that was needed. I have no time to go through the proof, but here is one very simple looking matrix result, which we were surprised to learn that any arbitrary NND matrix V naught can be expressed in this form for some matrices T and U. We had to prove it, repeat again and again, and to be convinced that it is correct. Another related thing is that if A and S are matrices, S is symmetric, then these statements are equivalent. A prime is non-negative definite, then it means that ASA prime can be written in this for some n. That is very helpful, but I'm not sure if we were aware of these tools before doing our stuff. Then third lemma, simple matrix lemma, but somehow new to us. If A and B have column spaces disjoint, then the following two statements are equivalent. The sum is non-negative definite, and the items in the sum are non-negative definite. Then there is so these were needed while going through the proofs, and as I said, it doesn't make sense to go through the proofs, but they were definitely needed. Then there is a separate corollary, very important, namely, if we consider these two sets, this looks familiar. We have been seeing this matrix in many times. But if we consider such set where we have this sigma squared here, then, and sigma squared is fixed, then these sets are not identical. The equality them holds only if green V is above sigma squared V naught in Löwner sense. That took us some time to get fixed. Here I have the last section. That is a summary of the main statements repeated in simplified forms. And we may almost only admire these equivalent statements because I think there is nothing wrong in them, but they have been, I have mentioned them earlier, but this is the one way to simply have a look at them. Another way, the following statements are equivalent, but here we have V naught. But they are not equivalent. C and D are equivalent only if this Loebner ordering between these two matrices is holding. Okay. This is the end of my technical talk. And now I utilize the opportunity to say some non-technical facts. I'm talking about K. Manjunath Prasad, Manipal University, some flashes of his life, let's say. He looked like this 32 years ago, if you are interested. Not bad at all, I would say. I met him in Bangalore, 1993, when I was touring around India for a couple of weeks, and he was hosting me and my daughter there in Bangalore, ISI. And here is my daughter, who is also now 32 years older, like Prasad is also the same amount of years older. Actually, I met Prasad 1 year earlier, 92. In Delhi, we had a workshop on generalized inverses, and you can easily recognize the young face here. This is this guy is Robinson, and I remember George Steyan used to call his wife Mrs. Robinson, which was quite correct, but there was a song which inspired George so much that he decided to call him with full name. C.R. Rao, S.K. Mitra, John Chipman. None of these guys is anymore among us. Bhaskara Rao, who has been important guy in Prasad's career, 2012, and Steve, we prepared with Steve this nice poster, 2014. One day we were standing the afternoon and keeping this up. And this is not that bad photo if I say it myself. This was taken in Poznan, 2017. And this is really my last slide. And I wish to express my sincerest thanks to Professor Prasad and his team for putting Manipal into the mathematical and statistical map. Thank you, Professor Prasad. Don't even think about retiring. Thank you.
Thank you, Simo, for the technical and non-technical insights. So first off, let's have questions or comments on the mathematical side.
I am Megambaram. Hope
Hello?
you remember me. So I have a paper in special matrices in 2024. It is disjoint sections of positive semi-definite matrices and its applications in general Gauss Markov model.
Mm-hmm.
There, I don't know whether you have gone through that paper. There I have used what is called the inverse rank complementary matrix method for decomposing the covariance matrix, variance covariance matrix G into disjoint sections, into disjoint matrices. By that approach, I am able to decompose the random variable y in the GGM model into 4 components as y is equal to y1 plus y2 plus y3 plus y4. This y4 is equal to 0 with the probability 1. Y3 is a constant vector v. It's a degenerate random variable. And y1 is that part which contains all information on x beta. So with that decomposition, we can easily show all these facts about V, V naught easily. And your question regarding one particular problem, how V is equal to V naught plus etc., where the two matrices R and S are arbitrary symmetric matrices, there I also feel that we cannot take any arbitrary symmetric matrices. If you take, we have to be cautious so that V naught is always bigger than V.
Yes.
V naught is a bigger component. V naught M is bigger than V. So that only we have to take care. If you don't take care of that, so it may, what will happen, V naught plus something, no, it will be equal to V naught. It cannot, V cannot exceed V naught M. It will almost be equal. That is why I think Rao has given that equation. So what I wanted to say is that my paper gives clarification to all these issues regarding blues, regarding this comparison of V and V naught, etc. That is my belief that we can solve these issues. If you have not gone through that my paper, I can send it. I can email to you.
Yes, thank you, please.
I will do it. I will do it. I will be happy to share. Get your comments on that.
Very good.
I'll be very happy. Oh, thank you. That is what I wanted to say.
Thank you. Further comments or questions for Simon? Okay, if not, then let's show him our appreciation.
I thank Professor Iclaa for chairing the session. So this brings us to the end of all the technical sessions. So now I request Ms. Aishwarya to take over for a valedictory session.
I have one announcement. Timo.
Yes.
Hello.
Hello. Yes.
I would like to say I'm keeping one more shawl for you.
Okay.
In 2030, I kept one shawl for you. Now I'll add one more and keep it with me. You'll have to come and collect it. Come and collect.
Fine.
Okay. Thanks for joining us.
Good afternoon, everyone. Now we have come to the valedictory ceremony of the International Conference on Linear Algebra and its Applications. It has been a privilege to be a part of such an inspiring gathering of scholars and researchers dedicated to advancing the theory and applications of linear algebra. I now request Coordinator of KRMS, Professor Manjunath Prasad, and Organizing Secretary Dr. Harikrishnan PK to escort the dignitaries to the dais.
Yeah.
We are now pleased to invite Professor Stephen J. Kirkland to address the gathering and share his valuable insights.
Thank you very much. So we've had several days here of exciting mathematics, insights, collaborations, and good fellowship as well. So what I observed over the course of the few days is that in addition to its core mission, linear algebra has many arms and a long reach into numerous branches of mathematics. And we've seen this well displayed at this conference, as there have been talks on, amongst other things, abstract algebra, copositivity, game theory, the linear complementarity problem, linear programming, mathematical statistics, network science, operator theory, quantum information theory, and spectral graph theory. The flow of ideas between linear algebra and other branches Safe? Okay. An event like Iclaa 2025 doesn't happen by itself. The dedicated staff and volunteers at CARMS have worked hard to keep our minds and our bodies fueled. Under the leadership of Professor Prasad, CARMS has once again given us an outstanding event that brings mathematical excellence together with generous hospitality. So let's take a moment to express our appreciation to our hosts. To those delegates from outside of Manipal, I wish you safe travels home, and I look forward to meeting many of you at a future installment of the Iclaa series. Thank you.
Thank you, sir. Now we begin with the certificate distribution for our contributory speakers. I now request Professor S.K. Jain to kindly come forward and present the certificates to the contributory speakers. Mr. Akash Kalita. Dr. Ravinder Kumar. Mr. Sangam Adabavi. Dr. Ishwar Mahato. Ms. Sarojini Mahapatra. Mr. Madhav Mondal. Madhav Mondal. Sinchana N. Sachin Naik. Aishwarya Nayak. Nivedita. Thank you, sir. I now request Professor Stephen to continue the certificates. Swarnalata Oja, Nagraj P, Prakash P, Hiran Maipal, Sovereign Pal, Sirshendupan, Smriti Pandey, Sirshendupan is not here. Smriti Pandey, Saurabh, Rashmi Rekha, Shweta, Shweta Patra, Akash Pradhan, Akash. Thank you, Professor. Now I request Professor S.K. Niyogi to hand over the certificates. Askar Ali, Dikshita Vivek Anchan, Anusha, Anjita Ashokan, Sridhar, Anjali Beniwal, Kaushik Bhakta, this is Anjali. Pranisha Chetri, Sunil Das, Shahista Hanif, Aditi Havaldar, Maitri K, Shivarama KN, Gopika KV, Madhumita KV, Thank you, Professor. I now request Professor Manjunath Prasad to hand over the certificates. Dashna, Sailendra Pradhan, Samapti Pratihar, Renjini, Pavan Kumar, Partharana. Pawan Kumar. Bhagya Jyoti Rao. Shashwat Shetty. Manideep Saha. Shubham Saha. Piyush Sharma. Subramanya Shanai. Shiva Prakash. Aditya Singh. Divya Devi T. Shweta Yadav. Thank you, Professor. I now request Professor Harikrishnan to hand over the certificates. Jitul Talukdar. Kurmaya Tamminana. Divya Taneja. Tem Jane Sangba. Matthew Thomas.
Joo,
Vansinath Tota.
jakaa niille oppilaille todistuksia.
Kavyalakshmi Upadhyaya.
Joo.
Bhagyalakshmi.
Olin ei mä näy tuossa.
Mamta Verma. Tikesh Verma. Dhanyashri Vinay. Sajal Ghosh. Gopika Govind. Mahendra Kumar Gupta. Neha Gupta. Srinath Hadimani. Thanks. I now request Professor S.K. Jain to address the gathering.
Well, I'm extremely pleased to see all these 4 days of presentations, talks, and enjoying the hospitality. It has been a great pleasure for my wife and for me. Today, my wife was saying, I'm very pleased to see all this thing. And she was the other day at the beach, and she said, well, this is something which is exemplary. Anyway, academically, I am highly impressed. I cannot tell you how much. It's immeasurable with the dedication and the presentation of all of you and the talks, invited talks, and presentations. He has been a great. Looks like to me, Manju Prasad has been really been busy all through every moment, even in sleep. He has been working so hard, and I know he's how hardworking and I would say mathematically so strong person he is. I know him since 1980s or 90s, and his encouragement, his drive is immeasurable. I only wish all of you the best of luck, best of my wishes, and I pray to God that you further prosper in life and continue this practice. Thank you.
Thank you, sir. Now, I would like to invite Dr. Harikrishnan PK, Organizing Secretary, ICLAA, to deliver the vote of thanks. Yes, sir.
Yeah, now I like to inform you all. One more thing. Okay, thank you. We always had the practice of having publications, at least one. At many occasions, it used to be more than one. And keeping that tradition this time also, though initially we were little reluctant, with the encouragement of everyone, we are thinking of going ahead with some more publications. One with the prominent Journal of Algebra and Applications. That particular journal is somewhat specialized. You can go to the journal site and find out. And if you have article common in the focus of conference as well as journal, please make submission. If you have any article with a little deviation, but within the focus of conference, please make submission, and we will after do revision process. It could be published in Springer volume, probably ISI series or CRR series.
Or any other similar thing.
Yeah, CRR series or ISI series, most probably ISI series. Please don't get disappointment this time, and we will be going ahead with this publication. And you are welcome for submitting. Okay. And one more thing, again, I like to say that this will go through standard review process. Please don't get disappointment in case. Okay, I don't. You are welcome.
Good afternoon, everyone. On behalf of the organizing committee, it is my pleasure to propose the vote of thanks to this gathering on the occasion of the validatory function of ICLAA 2025. First and foremost, I would like to express my sincere gratitude to our Vice Chancellor for presiding the inaugural function, and Professor S.K. Jain and Professor T.S. Raghavan, Professor Stephen Kirkland, Scientific Chair of ICLAA 2025, and Professor Simo, and all other invited speakers from India and abroad for sparing their valuable time and delivering insightful lectures that greatly benefited our young researchers attending this conference. I would also like to thank the Head of the Department of Mathematics, MIT, and Head of the Department of Data Science and Applied Statistics, PSPH, for their kind support throughout the conference. My sincere thanks to all the delegates who traveled from various parts of the country to attend this conference to present their recent research findings before the experts in their respective domains. And I should especially thank to our organizing team member, Dr. Sachin, for efficiently managing the transport and accommodation arrangements for the speakers as well as the participants. And I also thank Dr. Srinath for smoothly handling the registration process and ensuring the technical sessions were conducted on time without any further delay. And I am not mentioning the name. I extended my heartfelt thanks to our research scholars. Many people are involved in that one, from mathematics department as well as statistics department, whose dedicated support was a key factor in the smooth conduct of the conference. Though I also express my sincere gratitude to MIT and MAHE for their generous logistics support, and especially to the KEF R&D Center for providing an excellent venue for the conference. Also, we are gratefully acknowledge the financial support from the DST, ANRF, and INSA. Finally, I express my sincere thanks to our co-organizing secretary, Dr. Varun sir. After the major accident also, he is full-time here to support us. Yes. And once again, I thank everyone who contributed directly or indirectly to making this conference a grand success. I hope that we will meet again for the ICLA 2027. Thank you. Okay, I should thank the International Linear Algebra Society for their endorsement for this conference. Thank you.
Thank you, sir. Thank you once again to everyone here for your presence, participation, and contributions. Wishing you all safe travel, continued success in your work, and joyful memories from this conference as you return home. Participants, please note, certificates for participants and attendance certificate will be available for collection at the registration desk after this ceremony. Thank you.
You need some rest. No, after didn't start at 6 o'clock. What time there? So it's 10 o'clock. So then we can confirm to the driver. That's it. You can inform them.
Yes, yeah, thank you.
Thanks for your help.
Yeah. Thank you.
So now ನಿಂದು text
ಇಷ್ಟು ವರ್ಷ ಬಂದಿದೆ ಒಂದ್ಸತಿ ಟ್ಯಾಕ್ಸ್ ಇರ್ಲಿಲ್ಲಪ್ಪ.
I feel so. Special bag issue they enroll will. No, otherwise, everything should get done there. Only these things. Yeah. Yeah. You tell them only 6. Well. Yeah. Okay. Take it off. Anyway, we'll be in the yeah, sure. We were talking. What time is this question? I think we're there. You're going tomorrow? Oh, please. See you, I say, hopefully. No, I will not be there. Oh, when I'm coming here, not anyway, you'll be. Yeah, that is actually just doing donkey in the sense. I then he was there. He joined it. Yes, not that paper. Yes, I will send a PDF. In fact, if you go to my website, all the papers are there. This is was in 1965. You can you'll get it. Very good to me. Yeah, yesterday and today. We did our best.
So much food, so much